So I am going to record this for future, get everyone an email about where it's located. I'm hoping we can get it up on YouTube and be able to share that with a broader audience once we get done. But again, thanks everybody for attending. Glad you all could make it. We're going to get started pretty much right at 10. It's a rapid fire style. There's not going to be any introductions for the speakers. We're going to get right into the content. And again, I'm asking if you could use the chat to put questions in that you might have, and I will moderate the questions at the end. Um, so yeah, please see what Chris is saying there. Okay, very good. Got it. Okay. So yeah, if you could just use the chat to put your questions, and we'll try to get as many of those answered as possible. Each presentation is 15 minutes, and then we have 5 minutes for Q&A. Again, this is the state of research for compliance with PFAS regulations for surface water systems. Welcome, everyone. We're going to get started pretty much right at 10:30, and I'll turn it over to David Cornwell in less than a minute. So, welcome, everyone. Glad you can make it. Again, for those who are just joining, please put any questions in the chat. Not going to really do any um, not going to really do any live folks speaking just in the interest of time. So just put any questions you have in the chat. So with that, I'm going to ask David Cornwell to begin our webinar. Really excited to get this underway. Thank you, David, for presenting, and feel free to take it away.
Thanks, Albert, for putting this together, and welcome everybody. Hopefully I don't get us behind to begin with, right? Just turn me off, I suppose. So I changed my title slightly to Interesting and Innovative PFAS Treatment, because not everything I'm going to talk about is innovative. In fact, I'm going to talk about GAC and ion exchange a little bit. But I think it's interesting, not entirely unexpected, but a lot of information that I don't believe we hear about too much. So let's see. Okay. Well, we'll talk a little bit about NOM fouling on PFAS removal. How does loading rate affect GAC performance? I'd like to also talk about anion exchange for large surface water plants a little bit, some PAC considerations and potential for foam fractionation. So we'll just hit the high points of several of these items and show you some of the things that we've been finding. First of all, this is some work done at Passaic Valley Water Commission. This was Jim Mueller, I think, is going to talk, I think it's tomorrow, on some of the overview of what they're doing and how they're handling this project. But this is some pilot testing they've had us doing for quite some time on GAC. And the first thing we did in what we called phase one is we looked at 4 different carbons, and we tested empty bed contact times of 7.5, 15, and 20. I'll talk about that in just a second. And all this testing was at 2 GPM per square foot, below what you might actually design for. And we came up with these. Of course, everyone on here knows 15, 20 minutes being the traditional empty bed contact times used or recommended for, in this case, PFOA. PFOA is their limitation. They have PFOS over the level also, but PFOA is the limiting compound here. None of the short changed. We wanted to go down to 7.5 minutes because there is literature that suggests that the critical mass transfer zone is about 6 minutes for PFOA. And certainly there could be some advantages, but we were also concerned there could be some problems at a surface water plant with TOC. So you can see, first of all, I'm just showing a traditional breakthrough curve. You'll see a few of these here. For PFOA, this is one of the 4 carbons. I plotted this as actual concentration, and we've called the detection level 0 in this particular slide, as you can see. And this is showing the breakthrough curve. So the first thing to note is at this 7.5 minute empty bed contact time, PFOA was removed below the detection level. quite successfully. So we were above that minimum mass transfer zone. And also you can see where the breakthrough occurs, depending on where you want to call it here of here's our 4 level, and maybe you want to go up to a 3. So you can kind of see call breakthrough curve somewhere in this early 30,000 bed volumes for that. Let's look at now what happened at the other empty bed contact times. I'm showing all 4 carbons here. This is the one down here in this bottom right is the one we just were looking at. You can see the gray here is the 7.5 minute. And then look what happened. We went to, it's called mid, the 15, that's the middle port. That's the 15 minute is in the blue here, and the 20 minute is in the red here. And you can see that a couple of things happened. One critical thing that happened is the bed volumes got smaller. Less, if you will, less carbon utilization, quicker bed volume breakthrough as the empty bed contact increased. That's classical NOM fouling. I mean, as soon as you would see that, you say, we got NOM fouling going on here. One of the reasons that we tested this smaller bed volume. These were kind of just the general conclusions. You can see the ranges here of bed volumes treated for 7.5 up to 20 minutes and what that looked like just a little bit as we were doing our experimentation. The other thing that's going to be important as we talk about a little bit while I have this plot up here is you can see particularly at the 15 because we were kind of running out of time and effort in this phase 1, so we didn't get the 20 minutes all the way we'd like to, but you can certainly see at the 15 minute here, this curve is steeper. Again, not unexpected with NOM following that we're going to get a steeper breakthrough curve. This will be important in some of the data analysis as we go forward. As we moved out here a little bit, we get a steeper breakthrough curve than we got at most of them with the 7.5 minutes. So NOM following, where we're getting NOM following, I think this is kind of an interesting plot. I'm actually showing UV here. So we've got UV on the y-axis, and we've got the different contact times here. The red is the influent. Passaic Valley does a pretty good job in removing TOC, NOM. Their TOC going into a post contactor would only be in the 1 to 1.5 range. So we got following even though it was fairly low. And you can see quite distinctly here what happens with the UV and TOC. You can see a similar effort, but it's a little better spread out here. 7.5 minutes are these triangles. You can see that there's a little removal at the beginning, but as time went on, you can see that there's almost no removal taking half in 7.5 minutes, which is not unexpected for TOC, right? We designed TOC contactors that take 15 to 20 minutes to remove much TOC. And you can see as we move down here, we've got the X's is the 15 minute, certainly below, more is coming out, and we've got the blues here at the 20 minutes, more is coming out. So we certainly were taking out, especially at these higher empty bed contact times, quite a bit of a fair amount of the NOM, and that was causing follow in the micropores, and we weren't getting as efficient carbon usage. So what does that mean if we design for longer time than where we have NOM falling? So because 7.5 minutes is not traditional, right? We don't usually design PFOS, PFOA according to literature for 7.5 minutes. And I will say New Jersey DEP has been very cooperative with us in Passaic Valley as we move forward to decide. They haven't decided what they're going to do yet, but as we move forward. But what would happen here if you had the same mass of PFOA removed as you increased empty bed contact time where you got fouling? You'd of course have poor GAC utilization, meaning you have more GAC regeneration because it's less bed volumes being treated. Practical sense of that, more truck traffic, more pounds of GAC being regenerated, and a higher regeneration cost. So all of this results in generally higher regeneration, more traffic, more pounds if you are breaking through in terms of bed volume sooner for the same mass of PFOA removed. This is what this looks like. I want to talk about something else that you all may want to think about if you're groundwater with TOC or a surface water with TOC, especially if you didn't pilot and just chose, I'm going to design 20 minutes, or you piloted, but you only piloted at 15 or 20 minutes, and you may have not seen the impact of this fouling. This is the bed volumes that we had for the 3 different contact times. This is what happens if NOM fouling keeps getting worse. So let's say I designed for 10 MGD, but I'm only operating my average day at 5 MGD. I have all the contactors turned on, so I'm actually operating at a 40-minute empty bed contact time, right? Well, if NOM gets worse and worse and worse as I go up, and it stays this exact same slope, I could be way down here below 10,000 bed volumes. And there's just quickly, some indication that it's going to get worse. You can see here that the fresh carbon at 20 minutes was way down here in UV. So if I had 40 minutes, more of the bed is at 20 minutes or plus, I'm very likely to follow something like this. If it just stops totally, no more NOM following, it'll still be less, but it won't be drastic. So you could be someone here. The lesson learned is don't operate all your contactors if you have NOM following. Keep that turn off contactors and try to keep that EBCT down. I want to remind everybody about the benefits of blending. This is again the example for Passaic Valley. They have a situation where an average day they might have 6 to 7 of their 10 contactors, depending on what the final design looks like, going through this. And here's the breakthrough curve, the same one we've been looking at that may be done again, exactly where you cut it off could be done somewhere in this 35,000 bed volume range. If you do blending by staggering the operation, right? First, you advantage they don't all stop at the same time. I don't have to regenerate them all at the same time, but you also spread that out so that your blended water going out of the plant never meets your goal. And now I'm up about bed volumes here into the 60, 70,000 range, almost doubling the bed volumes by operating with blending. So don't forget that. You may be doing it, but if you're just cutting these off here, instead of looking at your blending situation, you may be using carbon much faster than you need to. And then finally, the last thing on carbon I wanted to talk about, we know this from the literature, that when you have a micropollutant and you are increasing, or if you keep the same empty bed contact time, but you increase flow rates, loading rates, you should get the same breakthrough curve with a micropollutant because it's micropore limited. And I'm just showing here, we did test. Our original was at 2 GPMs per square foot. We tested 4 and 6, 4 being the purple, green being the 6, and all the others being 2 GPM per square foot. Very, very similar breakthrough curves. You're always going to get some differential, but very similar ranges as we get into this 4 range. And it just means it's so impractical to test 6 GPM per square foot at 20 minutes in contactors because you need 2 or 3 of them in series in a pilot plant. So much easier to test lower flow rates, and then it should be the same going forward. Anion exchange, just a little bit on anion exchange. Normally, as you all know here, that this operated in pressure vessels, but are limited to about a 12-foot diameter. Guidance also says for a surface water plant, use pre-contactor cartridge, some kind of a cartridge filter ahead of that to take out small particles. For a large plant, both of these are impractical. You'd have a whole farm of vessels out there. And so we went ahead and said, hey, what the heck? We're going to test gravity without pre-particle removal. We had some indication gravity would be fine. We didn't know about the pre-particle removal not being used. You can see here, these are still running. And we're now at almost 140,000 bed volumes with 2 different anion exchange resins that we're using. So far still very successful in those operations, and we'll see where we get into in terms of a breakthrough anion exchange. But again, this is our gravity, 6 GPM per square foot, empty bed contact time of 3 minutes. I want to talk about PAC just a second here in my last couple of minutes. First of all, PAC products perform differently. So if you're going to rely on a PAC fed into your coagulation system, and I'm sure most of you would, you certainly want to look at different products. And here, the way I've reported this is nanograms removed per milligram of PAC. And you can see we have some products are way down here at 0.06, going up to 0.23, 0.26. So first of all, pick a good product. Secondly, what I'll talk about is the possibility of recirculating the PAC. We know that the PAC in a one-pass system is not utilized very fully. So what we did in the laboratory is just did a series of testing where we either did a pre-contact tank or just rapid mix, added the PAC into there. We found rapid mix worked pretty well. Go ahead and do your coagulation, do your flocculation, sedimentation, take the sludge off the bottom, recycle it. In this case, it was an iron coagulant. Recycle the PAC and the iron back around to the front end, and you have your treated water come off. And let's see what's going to happen when we do that. Well, what happened is we found here the utilization went way up associated with recycling the PAC. If we just had a one pass, let's say we had 10 and a one pass, it's about a 32 dose coming in at 10. Dose required to reach our goal is about 32. If we go in here at 10, it's only about 20, 21 by recycling. What's really interesting, and I think this will surprise some of you, if you look at the PAC utilization, its loading rate, if you will, with recirculation, it's about 0.35 nanograms per milligram for this particular carbon we were using. Okay. If you look at a GAC utilization, this is the 20-minute of our work, and this is the 7.5 minutes of our work. The utilization is 0.3 to 0.5 nanograms per milligram. In other words, we always think PAC is not practical, not useful. Well, the pounds used is pretty close to the same, which is kind of amazing. So PAC might be something you still want to look at. Obviously, you don't have to build all those contactors and things. Last thing I want to talk about here is our, I guess I've worded as Cornwell, we're excited about the possibility of foam fractionation. And Temple University, if you get a chance, look at some of the things they're doing. I don't know if anybody from Temple on this today. They've been doing exciting things. I'm only aware of one company trying to work on this, which is Invicta. There may be some more, but they seem to be the one that are out there for the most part. One of the interesting things, according to Temple University, is we could not only remove PFAS with foam fractionation, we can remove microplastics, which is a really nice benefit. It's applied up front, makes monitoring and pumping easier, no chemical addition for foam fractionation. And again, in Invicta's case, they destroy the PFAS and pretty modular for easy scale up, but nobody's doing it yet. I just stole this from Invicta. I'm not trying to advertise them, but I need I guess I am kind of, but I just needed a schematic that in their case, you have the removal here. They concentrate it quite a bit. And then whoops, that's my phone. So I'm almost there. In their case, they have a destruct system, and they like to recycle that. And therefore, there's no discharge whatsoever from this system. And it comes in with the source water and goes off to the water treatment. So it's applied right up front with your low lift pumps to go through it. If you're removing the microplastics, you probably don't want to recycle it. So you might want to come off of this concentration system and discharge this in some way. It has no PFAS in it, but it could have microplastics. Where do they go? I don't know. It's something we have to figure out, but I find that quite interesting. So my summary for today, this morning, to get us all started is unfortunately, the compliance window is very tight. And that means for utilities, they have limited time to explore and develop new technologies. I wish there was more time. But if you got to start designing, installing things, you can't start studying things very well either. There's some utilities might be able to use short-term compliance measures to allow technology to catch up and not build massive GAC contactors or something like that. Maybe PAC is one of those things that could work. I pointed out some of the issues to keep in mind if you have NOM for GAC. And just very interesting conflict. One conflict is optimal PFAS removal is achieved when TOC is not removed, right? But EPA is kind of thinking we're going to get a dual benefit here of PFAS and TOC. If you optimize PFAS, you won't get TOC. If you optimize TOC, you're really going to be using up carbon for PFAS. So anyway, I thank you all for your time. And I was pretty close, Albert, and
Fantastic. Yep.
got you going.
Right on the money. Good job. Thank you very much. We have a couple of questions. While we're getting into the questions, I'm going to just ask, you already did it. Stop sharing, and we'll let Eric start sharing. He can get his slides up. Welcome, Eric. So a couple of questions. The pack that you were talking about, how was it applied? As a slurry? How was pack applied?
Well, Pat, we did the pack, of course. That's laboratory work. We do slurry at first because we want to get it pre-wetted. If you're in a full-scale plant, I like slurries. you could use a slurry PAC stem, or you could dry feed it if it's you've got some mixing for it ahead of time.
Okay, and the other question, did the anion exchange media require backwashing? What was the frequency and head loss buildup? Was chlorinated water used?
Good, very good questions. No chlorinated water on these particular resins. It does have to be backwashed. And we kept one of the reasons we kept the loading rate to 6 GPM per square foot is the head loss with the ion exchange gets pretty high. It was quite reasonable at 6. It was in the 3 to 4 range. I think we could have gone a little bit higher than the 6, but that's also probably where GAC would be designed. So the contactors could be almost the same contactor for GAC or ion exchange. I don't have the frequency right in front of me. I want to say that was in the 4 to 6 week range where we did have to backwash and we keep it below fluidization velocity, just like GAC. And so it did require backwashing, yes.
Okay, and last one for me is any evidence of fouling of the media?
Yeah, very little. For you talking about ion exchange, I
Yeah, an
assume.
exchange, yes, yeah.
Yeah. I could have shown that. I didn't think I had time, but the TOC UV removal with a 3 minute empty bed contact time in ion exchange was very low. And so we have not seen the fouling.
Yeah,
It wasn't anywhere near what it was at 15, 20 minute GAC. So it
okay.
could be that low EBCT has kept the TOC fouling down.
Well, David, thank you very much. Thanks for kicking things off today with talk number one. We're going to shift gears and welcome Eric Rosenfeld. Welcome, Eric.
Thank you, AJ. Are we ready to go?
Ready to go.
All right, let's get going. Um, so I'm here to talk about supporting PFAS treatment decisions, particularly in surface water plants, trying to compare treatment options with both cost and non-cost considerations. Clearly, this is something that a lot of utilities are facing. I'm just going to talk quickly about some basics and then go into a couple of case studies. Before I start, I want to acknowledge these particular projects. There's kind of an amalgam of a bunch of projects that we've done throughout kind of Virginia and the Carolinas and Tennessee and Georgia. And they're related in that they're surface waters and they're challenging surface waters. A lot of the organics um, that Dave was talking about. And then, of course, want to talk about a couple of partners. We've worked a lot with Black and Veatch. We also are working with Hargit LLC and One Water Engineering on several of these projects. So PFAS is a national drinking water challenge, but there are certainly some surface water PFAS hotspots out there. Ohio River Valley, North Georgia and Alabama, Carolinas and Virginia. Some of the Texas areas are really mainly, not all, but mainly where the surface water challenges have been showing up, at least in our experience. And we do have quite a bit of experience. We've got a lot of projects nationwide, but we've been able to do a fair amount of projects in these sort of surface water hotspots around the country. And what have we learned? Well, we've learned that surface water treatment for PFAS is somewhat unique. Some of the things that Dave talked about are certainly lessons that we've seen. But a few of the big things just to keep in mind is that the water quality in these plants are often variable, wide ranges over time and space, with everything related to TOC, algae, lots of other water quality challenges as well. In addition to that, our PFAS levels are often variable. So you may have, wide swings in PFAS from day to day in these surface water facilities. And another thing to think about is there's often already a robust treatment process in existence already, one that's been designed for surface water treatment. So a lot of these PFAS treatment processes have to integrate within that existing treatment plant. And so treatment selection must deal with whatever treatment process we use must be effective for PFAS, robust to variable water quality, and ideally provide multiple benefits, including things and challenges we face include plant hydraulics, often where we've got space constraints, of course, operability and constructability, and then funding these projects is always a challenge. So this isn't new for surface water utilities. They've been fighting the fight against water quality challenges for years. And often we can look at operational approaches for a lot of water quality treatment enhancements or infrastructure approaches. So a lot of things can be managed by tweaking current operations. Some of these things definitely need additional infrastructure added. And then there's this gray area where there's things that we can do operationally and infrastructure wise. And I'm going to loosely say that PFAS kind of fits in there. Typically, we do have to do some sort of infrastructure improvements, but the idea of PAC allows us an option that most utilities at least are familiar with, and many already have some infrastructure to deal with. And I'll explain that a little bit more. I'm not going to go through this. I don't have time, but PAC has several advantages, lots of potential concerns. GAC is another effective technology with a few more advantages and a few less concerns related to PFAS treatment. Ion exchange, this is sort of the similar, and then of course reverse osmosis in membranes is highly effective but significantly costly. And we've actually seen more of these high pressure membrane operations on for PFAS solutions on surface waters, which has been a little bit of a surprising observation over the first few years of PFAS treatment. So the first study I'm going to talk about is in South Carolina, and the question here is deciding on GAC, and it's really what factors went into understanding whether GAC versus PAC was the option to go with here. So this is an eastern lowland surface water. It is not an easy surface water to treat. Has lots of high natural organics, high manganese, lots of algae, taste and odor compounds, potentially some cyanotoxins as well. And then recently, of course, they found PFAS in these sources. There's two water plants here fed off a large river, and the water plants are connected through a canal and a series of reservoirs. And so both plants have challenges with all of these water quality issues, and we're looking for a solution clearly to address PFAS, but then also to look at creating a more robust process for some of their other challenges. So the PFAS challenge is something that we often see with a lot of surface waters. It is above the limit, but not a whole lot above the limit. So this is another thing that we've been seeing a lot with surface waters is rarely do you see anything above 10, but sometimes you might see a spike above 10 for PFOA or PFOS. So this system will not meet compliance without treatment, but it's not far off. So our client first underwent a rigorous technology selection process where they piloted advanced activated carbon techniques, both powdered carbon and GAC, as well as ion exchange. They decided against RO and nanofiltration membranes prior to piloting, but they definitely piloted GAC and ion exchange. Benefits for the activated carbon were that both provided effective PFAS control, GAC provided robust current and future contaminant control, and then, of course, there was flexibility in how to deploy it. The concerns they identified were operational intensity of PAC, and of course, on the other side, GAC was a more capital-intensive process. So they decided to employ either PAC or GAC to address PFAS and additional water quality concerns, but we had to help work through that process of GAC versus PAC. So the first thing we did was looked at the benefits of powdered carbon versus GAC. And there was another option that they looked at, but this became expensive and didn't see a whole lot of benefits over the other two. So powdered carbon was effective for their PFAS challenges. It was effective for algal-related taste and odor, less effective for DBPs in the testing that we looked at. Didn't provide quite a solution for manganese, distribution system, other things were not quite as addressed, but it was significantly less expensive. PFAS or GAC for PFAS was very effective, good for algal-related taste and odor, excellent for their DBP challenges. It allowed them to chlorinate their existing filters more aggressively, so it opened up an opportunity for manganese control, better manganese control, also distribution system discoloration as a result, and then there was some other added benefits. So we got lots of benefits. We can see lots of benefits for GAC, but the challenge, of course, is that GAC is significantly more expensive. So we weren't going to get our way out of here on a life cycle cost benefit analysis or a life cycle cost analysis Even though powdered carbon required some improvements for residuals and it would be an operationally intensive process, it was still significantly less expensive. So how could we work with the utility to create a situation where clearly the benefits were outweighing the cost difference? And we did this through an MCDA process, multi-criteria decision analysis, where we talked with the client and we weighted their economic, regulatory, O&M, and then community benefits and costs in a MCDA analysis. So you can see that yes, economics were of concern for them, but it wasn't an overwhelming concern. So it came out to be about 31% of their concern pie, and the other options like regulatory and community were really the ones that lifted the analysis. So at the end of the day, we were able to come up with an analysis working together with the utility and the decision makers to understand that the water quality benefits that they'd see with GAC clearly were more important to them than the cost challenges they would come up with. And so the decision was to go to GAC utilizing this transparent cost benefit analysis approach to make it clear that they could see the benefits of those additional water quality and that was important enough for them to overcome the significant cost differential between PAC and GAC. So the second study I'm going to talk about is where we came up with one for a client where we came up with the exact opposite solution, right? So this one decided on PAC, at least for the short term, and this got to Dave's idea of let's implement a short-term solution where we might be able to do some things in the longer term that could allow us to avoid a more capital-intensive project. Again, this is a Virginia utility, a large utility, 125 MGD, and they have PFOA and PFOS in their finished water, but also in their source water. Averages are slightly above the limit. Their maximum doesn't even get up to 10, but especially for PFOA, they're above 4.0 nanograms per liter 82% of the time. They do have additional PFAS chemicals that are detected, but they developed these solutions for PFOA and PFOS at this time. And you can see again where I talked about highly variable from day to day, from week to week, from month to month. There's significant changes in PFOA, PFOS, but also other water quality challenges, other water quality concerns as well. This is a robust treatment process. It has ozone and biological filtration. And we were really looking at three different options, whether we could put in powdered carbon up front, post-filter GAC or ion exchange, or replacing the biological filtration with filter adsorbers. The PAC advantages to that, again, least expensive capital option. It's coming in right now. It's under design, and a little bit of a spoiler, it's about a $20 million solution. The PAC has to be fed at 25 to 30 milligrams per liter, and it can effectively remove 40 to 50%. Concerns that were in the mix include long-term PAC disposal concerns. They may impact the ability or their current residuals handling processes. We still are working that out. And then an operational strategy is yet to be determined. Clearly, with that wide variability, sometimes above, sometimes below the limit, we would like to be able to at least understand and increase and decrease our PAC dose as appropriate to save some costs. GAC has its advantages, as does ion exchange, and there's significant costs and other things related to those as well. We did see a difference with added detention time. So if we fed at the intake versus at the front of the plant, we got about a 20% dose reduction in PAC. We did a full-scale test, which was really interesting. We looked at half the plant and fed PAC up front, and we saw about 46% PFOS removal, 35 to 40% PFOA removal. At the end of the day, we came up with a PFOA removal rate, which was our target of about 41%, and PFOS was a little bit better with 25 milligrams per liter PAC. And moving forward, there's several things that are going to happen here. So they're moving forward with the PAC design and construction. So that's going to be a short-term solution. But in the meantime, there's lots of things that can be done in terms of source water protection, additional research looking at other treatment alternatives, and then even some legal action to understand the long-term solutions. And the final thing I want to talk about is this is a really interesting system that a lot of people probably know about. It's located on a reservoir that has an advanced wastewater treatment plant up front. And there's lots of places that have been identified as potential PFAS sources. And we're currently working with the Water Research Foundation on what we call the One PFAS project, looking at a system-wide approach to managing PFAS chemicals and trying to understand whether um, where are most cost effective to provide the most benefit to the entire system would be considering improvements at the water treatment plant, considering potential PFAS related improvements at the wastewater treatment plant, or even considering potential interventions um, throughout the entire watershed, more stormwater type interventions to understand if maybe this pack solution is the right solution for long term because we can find ways to really reduce levels in the source and throughout the system, or even to look at treatment options that might be more beneficial if they're applied upstream somewhere in either at the wastewater plant or even in their collection system with significant industrial users. So keep an eye out for the results from that one PFAS project in the next couple of years. So in conclusion, surface water treatment for PFAS is relatively unique. There's a lot of things that are needed, including a barrier that can effectively treat PFAS and handle all sorts of changes in water quality, and also manage potential hydraulic challenges and site constraint challenges, things like that. Surface water systems are often larger systems than groundwater systems, not always, but sometimes, but often, and therefore size and scale of effective treatment plants are really important to consider. And then there are operational approaches, high dose pack, infrastructure approaches like GAC, ion exchange. And then, as I mentioned, membranes seem to be gaining traction in surface water applications, which has been interesting to watch and be a part of. And then when deciding between technologies, both cost and non-cost factors, non-economic factors can play a role and can lead you to very different solutions based on, of course, the desires and the philosophies of the client of the utilities. And then multi-criteria decision analysis can be helpful in making this. And then finally, in these surface water systems, it's important to remember that active source water control can hold the key to cost-effective PFAS compliance. We're typically not well above and not consistently above the 4 part per trillion limit. And there are opportunities if we can work together collaboratively. It's not easy, but if we can find ways to work together collaboratively, there might be opportunities to save, to really come up with effective holistic solutions and save ratepayers significant amounts of money. So with that, I think I'm wrapped up, AJ.
Good job, Eric. Thank you. We do have a number of questions. We'll try to get to the ones we can. While we're doing that, if you don't mind, just stop sharing, and then Adam can load up his
We'll
slides.
try to do that.
All right.
Need some
First,
help.
first question is, why did you not consider filter top
Ah,
chlorination for manganese control with the pack, or did you? And
we did. There's a series of challenges that have been going on. We didn't see that we got enough TOC removal to really save the day, and we are chlorinating on top of the filters. It's just we can't go as crazy about it, and it doesn't become as robust. And we've got some other challenges there too, including low filter pH and things like that that need to be addressed.
yeah, looked like there were other water quality issues. So
Yeah.
next question is, what do you do with the pack GAC after it's spent? Any common
So
ways to treat them?
So it's great. So the GAC, that's one of the major advantages is there's opportunities for thermal reactivation, other types of reactivation, and those have been shown to have some benefits in terms of destroying PFAS if you do it right, if you employ the reactivation process. Powdered carbon is clearly something to consider, and I don't have a great solution. It ends up being intermixed with a lot of the solids of the treatment plant, and we have to think about those impacts and if those might end up getting regulated. We have seen a few utilities that will try to do a pre-sedimentation process and try to get some of the pack to stay there, and so that it becomes an issue that's not intermingled with their full plant residuals, but there always seems to be a little bit of carryover and a little bit of PFAS that ends up in those.
Okay. Yeah, and we do have a presentation coming up on residuals, so stay tuned for
Excellent.
that. Next question. Can you comment on some of the hydraulic challenges that have to be managed with the different treatment options? I assume they're talking about different hydraulic profile, maybe pumping needs to be added for some options.
Yeah, definitely. We've found clear most surface water treatment plants were not built with 25 feet of hydraulic head between their filters and their clear well. So oftentimes we end up having to repump through this advanced treatment process if it's implemented in a post-filter application point, just so that we can build that up. Um, Also, hydraulically, things to consider. I showed on there changing out filter media to make it kind of a GAC cap. That can create some hydraulic challenges if you don't remember that your filter has to be a filter first,
Yep.
right? And if you do things like, we've seen some clients get aggressive on the GAC media size and create themselves some hydraulics challenges across their filters when they were thinking only about PFAS removal and less so about, the hydraulics of their filter.
Okay, and then we have probably 1 minute looking for a little more on the one PFAS project. Maybe just a couple more details. I don't know. You could probably talk for 30 minutes on it, but or more. But what would you say in a minute or less that you
Well,
can
I've
add?
got I've got a little plug. We will be talking about it at ACE, but it's a collaboration with Virginia Tech and with a lot of stakeholders of the Aquacon system, and we're really searching. The crux of it is a real time of travel model that's been developed that allows us to basically tweak knobs of the various inputs of PFAS, and kind of through that to develop an understanding of um, what reductions in the watershed or reductions at the water plant or at the wastewater plant could do to reduce those numbers of PFAS. And then, of course, our part of that is we've got to cost all these interventions, and so we're going to come up with a laundry list of potential PFAS solutions watershed wide, costs of those solutions to the utilities, and then also costs of those solutions to the individual ratepayers, which is another complicating factor because a lot of these ratepayers pay bills to the water company and to the wastewater agency. So there's a lot of interesting dynamics wrapped up in that project. But I would definitely, suggest folks that are interested keep an eye on that project as over the next couple of years as we continue to develop it.
Great, Eric. Thank you very much. Thanks everyone for the questions. Just want to welcome Adam Pfeffer from Black and Veatch to present. I did want to make a quick mention of North Jersey District Water Supply Commission and thanks to them for sponsoring this webinar and supporting the planning and all that went into planning this. So thanks to North Jersey District Water Supply Commission there in Wanacue, New Jersey. So Adam, go right ahead. You can take it away.
All right, thanks, AJ. So I'm going to be talking about PFAS treatment at Sweeney Water Treatment Plant with a real focus on the kind of differentiating factors or lessons learned specific to surface water for the facility. I see here. Okay, so I'm going to start by walking through a little bit of Wilmington's story there and Cape Fear Public Utility Authority's background there, and then integrating the GAC contactors into the surface water plants and where they go and what was considered. Some of the startup and operations considerations, getting into a little bit of discussion about the media replacement approach, and then some of the key design and operational lessons from the plant. Just some of the background. This project, in a lot of ways, is kind of the OG PFAS project. It all started on June 8th of 2017 when this headline hit the local newspaper there, and it caused quite an uproar with the water system. The Sweeney Water Treatment Plant is by far the largest treatment facility for Cape Fear Public Utilities Authority, serves the majority of the system, and there is an urgent response that was required from the public response to this news. It's a 44 MGD surface water treatment plant, and to my knowledge, happy to be corrected, but to my knowledge, it is still the largest PFAS specific designed treatment facility in operation in the United States. There are other larger facilities that were designed for TOC removal for DBP reasons, but as far as I know, this is the largest one currently in operation for specifically designed for PFAS. This is showing some of the raw water data. This is a combined PFAS here, and this is in the years leading up to the design and implementation of the project. They were monitoring for 20 plus PFAS and had up to 1,000 PPT total in the river. So not small numbers. As far as we did do piloting and evaluation, and did end up on a GAC post-contactor solution. This is their process train, so it is a uses super pulsators for pre-treatment, followed by intermediate. It also raw water and intermediate ozonation, biological filtration with GAC. And then the contactors were thought it was best to fit into the process train after the biofiltration. We did look at just more frequent changeouts of their active GAC, but the changeout frequency was not feasible, particularly with the solids loading that was contributing to breakthrough, and also the backwashing may have contributed to bed stratification and some reductions in GAC usage efficiency. But we did that in front of the UV disinfection. As a side note, we happen to see dramatic increases in transmissivity, so the UV effectiveness went up as a result of the GAC contactors going in. And then the finished water chlorination, it is free chlorine, primary CT, and the chemical dose required for distribution system secondary disinfection would drop dramatically after the GAC contactors went in as well. Oh, I forgot the numbers. You can see each of the individual systems there, and it is worth pointing out the number 5 is the GAC contactors. They're deep bed contactors, and you can see how it, from a hydraulic profile, it kind of stands out because it's quite a bit of height that you have to work with to have the hydraulic grade line work with the gravity filtration there. So speaking of that grade line, Eric mentioned that you pretty much, very few surface water treatment plants are going to be designed with this much head kind of in the middle there. So in the vast majority of surface water treatment applications with PFAS treatment, you're probably going to be looking at repumping. So this grade line looks a little bit more like you might expect for a filter, where you have your operating head and that you're working with, and you have your clean bed and dirty head that is controlled by your hydraulic rate control valve that's at the effluent, and that kind of is your control. You gradually open the valve to maintain the target flow rate as you experience gradual head loss through your contactor runs. This is another way to do it to show that the same HGL considerations. This is identifying kind of the different changing flow conditions. With surface water, you are going to be more subject to temperature changes and seasonal variability than you might be for a groundwater system, and that has to be considered when you're looking at that head loss and trying to design for worst case conditions under gravity flow. So moving on to talk some about the operational startup. There's a lot of trucks, at least at this facility. If you don't have on-site conveyance, there's a lot of trucks that are involved with this. These contactors are quite large. As Carl Van der Maiden likes to say, that's not a small man right there. He's quite a large person. But when you have the deep bed contactors, it really helps show you the scale that we're talking about. And the media loading, something that some people might take for granted, is that when you are taking media away, it's wet. Wet media is heavy. And the limiting factor on transportation of the media is the weight for DOT restrictions on the road. So you need more trucks to load, roughly double the number of trucks to unload wet media as you do to load up that dry media when you're filling up these contactors. At least in Cape Fear's case, it's 2 to 3 days of work for loading the contactor with the slurry system in place there. And based on their water quality goals, they were very, very intolerant of any impairments to their treatment goals resulting from the GAC. So we had to wash away pretty much all the arsenic before we put these contactors into operation. So 6 to 10 days of backwashing for them, about 75 bed volumes before we were able to meet their TDS, arsenic, and pH water quality goals. So what that meant is about 2.5 months of prep total from when you start loading the GAC into the individual contactors until all of them are rinsed and ready, meeting the water quality targets for operation. And this takes a lot of strategy depending on where you're putting that water, if you're recycling it, if you're treating it, if you're sending it to an on-site facility for recycling or decant, or if you're discharging to sewer, and what are the restrictions by flow or by quality on that. So it is really advisable to have a pretty detailed strategy of how to handle that rinse water. It is, if you have a sizable facility, that ends up being a very sizable volume. As far as Sweeney's GAC changeout triggers, this was very interesting in that all of the planning and preparation and operations was done before even the draft rule was in place. This facility went online in October of 2022. And so it had to decide what was going to be good enough for the customers. And so that top line you see is a PRP acid. It was the first to break through. As far as like an independent health review, it's pretty modest. Modest impacts. The next one is the red line is the PFMOAA. That is distinctly associated with the industrial contamination from the Chemours facility that was upstream of this, and less known about potential health impacts. And so Cape Fear Public Utilities Authorities made the decision to change out their carbon based on breakthrough of this three carbon compound, PFMOAA. And that was a little bit of a noisy criteria. So what you can see here is they started tracking on a 12-month rolling average, and that gave them a nice clean trend to work with. What you are seeing here is some water quality impacts that they did better with their first run than subsequent runs, and so they ended up a little bit behind. What they would say is had to do some shorter changeouts. So I'm going to circle back to that here, but this was a screenshot of kind of the Gantt chart and planning for GAC changeouts, and there's a lot going on here. The main takeaway I just wanted to show is that there's a lot to coordinate, and it's not you have to manage your staggered breakthrough. David brought that up, and Eric did as well, is managing your breakthrough incrementally, so you're not having to do multiple replacements at once, and you can really fall behind if you don't have a good plan with that. As far as the cost associated with this, now Cape Fear did set that very, very aggressive changeout target. So these costs are a little bit more dramatic than you might see at a facility that's only treating exclusively for PFOA and PFOS. But the main takeaway here is that for a 44 MGD facility operating for PFAS on surface water, that the vast majority of the cost is associated with the carbon changeout. So any optimization that you can do of the media usage is going to yield the biggest bang for your buck as far as O&M cost reductions. Getting into the media replacement approach, I won't spend too long here because others have mentioned it, but staggering your breakthrough is extremely important, both from an operations feasibility perspective and from a media utilization efficiency perspective. You can see here, this is just a really coarse simulation showing that if you were targeting that 10 ppt PFMOAA threshold for changeout, and you were operating all of your basins in synchronously, then that would lead to about 6,000 bed volumes treated before changeout. But if you stagger them, then you hit that target at about 10,500 or closer to 11,000 bed volumes. So you get almost a doubling of your bed life by appropriately staggering your basins in this type of GAC configuration. This also helps with your startup impacts from arsenic and pH and TDS, and managing those one at a time versus all at once. As far as what the changeout process looks like, you do a GAC drainage. This is a photo of the carbon loading in from the conveyance structure. And the way Sweeney worked out the procedure is we did 3 lifts. So you add a couple trucks and then you backwash and drain again. Then you add a couple more trucks for GAC and backwash and drain. And you have to do that to make sure the media remains level. And there is a 11 to 15% makeup of virgin media that's required after each change out. And contractually, Sweeney was Cape Fear was able to recently introduce I think it was a 14, it might have been 15 percent cap into their regeneration contract, so they don't have to pay in excess of that if the regeneration does not go as expected. And I think this is a really important point here in terms of determining the redundancy of design. Sweeney operates on average below 50% of their design capacity. And GAC, their reactivation time is 45 to 60 days from the time that it gets removed from the contactor until the time it's available again. So, and they realize that there are significant operational savings from being able to receive GAC from trucks into a contactor at the same time that the trucks are taking out spent GAC. So coordinating the replacement of receipt and delivery of GAC yielded some really significant savings. But they could only do that because they had that space in between their average capacity and their design capacity. And so if you are a facility that's operating a lot closer on average to your design capacity, you should strongly consider like an N+1 or N+2 configuration to be able to coordinate those operational savings. This is something that's frequently overlooked in treatment plant designs for GAC is the runoff water from the trucks. This is what it looks like. It's nice and black, so you have to make sure that that's going to an appropriate place. If it goes to a stream discharge, that doesn't work out well. And also, it takes about 3 hours-ish for these trucks to drain after a slurried conveyance of GAC. And so having a dedicated spot for those trucks to sit and drain is really helpful so they're not clogging up the traffic for the next truck in line. So just a summary, getting to the end here of the key lessons learned. So surface water is more variable than groundwater, so you have to be prepared for the worst case challenges in variation. It's very important to understand your hydraulic grade line, and there's impacts to other processes like the UV impacts, disinfection impacts, potential CT impacts, and unit process performances associated with the PFAS treatment. In operation, you really need to have some good design for your truck traffic, runoff and conveyance connections to facilitate life for your operators long term. Balancing reactivation turnaround with your treatment demands is critical for design. So you don't want to over design, but you also don't want to under design and then be slammed for production capacity when you're needing to regenerate spent contactors. Have a real smart plan for how to deal with the water from up to 6 MGD in the case of Sweeney for each contactor replacement. Make sure you have a plan for staggering your breakthrough so that you have one contactor at a time, and that optimizing media life is really your big lever for minimizing O&M costs. And with that, I'll take questions if there are any.
Adam, thank you so much. Really appreciate it. We do have a few questions, and we got a little bit of time here. So one of the questions was, are they currently using PFOA, PFAS for breakthrough, or are they still using the original triggers?
As far as I know, they're still using the original triggers as of very recently. And if you did not see PFOA and PFOS on the trend, it's because they're non-detect at the time they're dealing with replacement of those short chain compounds. So they not even a consideration with the current breakthrough trigger.
Okay, next question is, how do you estimate the impact of the pH of the water going on to the GAC and its PFAS removal capacity? Is there an optimum pH? Do you detect desorption effects at a pH greater than 8?
So we didn't look at this in detail. pH impacts to adsorption performance were not considered practical in terms of they were managing pH for a number of other factors with regards to the coagulant dose and pH adjustment, chemical savings. And so the pH, when I was talking about the pH considerations, when you put in virgin carbon, the pH, when you first start rinsing it, is about 11. So you have to account for that impact during startup just for those 75 or so bed volumes. And a lot of times you can't discharge that, or it might have impacts to your treatment process if you try and put it into plant flow. So when I was talking about the pH impacts, we didn't study performance impacts associated with GAC PFAS removal so much as managing the short-term pH impacts.
Okay. Just before I get to the next question, could you stop sharing and we'll let Bruce Rittman, Bruce, if you can hear me, if you could just share your slides just to get that teed up for the next and final
Okay, will do.
presentation. All right, thanks, Bruce. So the next question, same questioner. Is there any consideration for what he's calling intermediate GAC refilling, like filling with 90% and then putting another 10% during returning bad periods where you only refill a GAC partly and then add the remaining volume in a challenging period? Is anyone doing that? Have you heard of that?
I'm not quite sure I follow. So there is a virgin makeup, so that there is virgin GAC that's added to every regen. But beyond that, I'm not sure if there's anybody who's experimenting with additional virgin makeup on top of what isn't meeting spec after reactivation.
Okay. Yeah, I mean, certainly you can follow up with Adam directly on some of these things. Last question. Well, yeah, the last question will be, how is the media backwashed? Is it, yeah, but here's specific. Does the media need to be backwashed for head loss? If so, is air scour used?
Yeah, the media does occasionally need to be backwashed. It is much more infrequently than filters. It was on the order of several weeks in between backwashes, and it is based on a fluidization target, and that fluidization target tends to restore 100% of head loss.
All right, so
no air scour.
One last question: have you seen anything? Have you had any experience with new GAC system turning biological, decreasing PFAS removal? Recognize a new system was constructed just downstream from existing back system. Any problems with non-biological fouling?
I think that to the extent that there is any minor influence of biofouling, it's pretty much mitigated with the backwashes, and I fully expect that when you're talking about these deep bed contactors, that there is biological activity that's going on in there. There's no way that you can maintain any kind of disinfectant capacity throughout the deep bed. So my assumption is that there is some biological activity but that's not necessarily resulting in fouling, at least in this instance or any other instance I've seen so far.
Okay. Adam, thank you so much. Really appreciate hearing about Cape Fear's experience. We're going to turn it over to Bruce. And just one quick thing on Bruce's presentation. You notice that most of the presentations have been focused on surface water. This is sort of a special guest speaker talking about some exciting new findings and what might come down the road eventually. So it's sort of new research. So Bruce, please take it away.
Okay, thank you, Albert. Thanks for having me, and I'm glad that I'm special. That really makes me feel good. And so I'm going to be special. We're going to talk about defluorination and mineralization of PFAS. So we're going to destroy it. We're not just going to separate it. We want to destroy it on that. So, I mean, I don't need to introduce this group to what PFAS is, so I'm not going to spend a lot of time on this introductory slide, except for I'm going to emphasize the perfluorinated ones because they're the ones that are most difficult to destroy. So it's your PFOA and your PFOS and their cousins. And so why are they so difficult? Well, there are a couple of corollary reasons. One, of course, is that the carbon-fluorine bond is the strongest bond known in organic chemistry. Its bond association energy, as you can see up on the upper left, is much larger than any of those other ones, and so it's hard to break. It's also a very polar bond, and that's because the element fluorine is extremely electronegative. Now, this on the one hand makes the bond very short and very strong, but on the other hand, it also gives us the possibility of defluorination and destroying it through a reductive process. So that's what I'm going to talk about here. Now, I'm the director of the Center for Environmental Biotechnology. I love to biodegrade things, but that's difficult to do here with PFAS, especially the perfluorinated one, because the CF bond is so strong. Plus, in the perfluorinated ones, the CF bonds are everywhere on the molecule. So it's really hard for the microorganisms and their enzymes to get access to the molecule. So this is really difficult here. So what we want to do here is we want to knock off some of the fluorine substituents. That is, we want to defluorinate it, and we're going to take advantage of the strong electronegativity of the fluoride element to do reductive defluorination. So that's what I'm going to begin with today. So how do we do that? Well, we actually do this in two stages. The first stage is just what I said, reductive defluorination. And as I will show you, we're going to use palladium-based nanoparticles to reductively defluorinate. And you can see there's a little example here. This is PFOA, and you use hydrogen, and you knock off some of the fluorines here and replace them with hydrogens. And now once you've done that enough, then the molecule becomes available for oxidative processes. And we're going to use microorganisms in what I'm going to talk about today. And they will do an oxidation process that will attack the carbon-carbon bonds as well as more of the carbon-fluorine bonds. And so when we combine these two things together, we can get the complete defluorination and mineralization of these perfluorinated compounds. So in the system I'm going to describe today, we do it in two stages. Now, the first stage is the hydrogen-based membrane catalyst film reactor. We're going to deliver hydrogen gas through gas transfer membranes. Deposited on the outside of the membranes are palladium-based nanoparticle film that is really good at reductive defluorination. I'll show you that. Then we're going to take those defluorinated compounds and deliver them over to an oxygen-based membrane biofilm reactor. Now we have a catalytic biofilm bacteria that are good at oxidizing and continuing to defluorinate these compounds. And so I'll talk about both stages on my talk today. So in the first stage, we're going to use palladium. Palladium is a very famous catalyst. And when you put it on the membrane here and you deliver hydrogen to it from the membrane, you get what's called activated hydrogen on the palladium. That's just a single H. This is extremely strong reactant. So that when something like PFOA absorbs nearby, it will then react to break the CF bond, releasing the fluorides and producing defluorinated compounds. And this reaction can continue so that you can produce a suite of defluorinated compounds based on this palladium-based catalysis. Now, we have to first form the catalytic film. It's actually pretty easy to do. I could show you some pictures here. It's a graph of how we do this. So when you look at the picture, the left-hand side is one of our columns with the membranes, and you can see that their membranes are white. We add a solution of palladium 2+. This is oxidized palladium. We added as palladium chloride, and happens to turn the water orange, which is very convenient because we can actually watch the reaction visually. So we start delivering hydrogen through the membrane, and you eventually form a few reduced palladium nanoparticles, and then those palladium nanoparticles catalyze further reductions of palladium, and you get what's called an autocatalytic process. So if you look down at the graph, the orange bars are the palladium 2+, and you can see it starts really slowly, but then the reaction accelerates until all of your palladium 2+ is gone, and you've got this big white bar with all the palladium on the membrane. And you look at the pictures, you can see that gradually the orange color goes away and it becomes clearer and clearer. And then you can see you got all these black nanoparticles on the membrane. They're very robustly attached. They don't come off. Now, once we have them in, then we can use it for PFAS reductive defluorination. I'm going to show you just one graph here. We've got hundreds of these, but this is a nice, easy one to look at. So here on the left side is a graph where we put PFOA in, and we deliver hydrogen, but there's no palladium, and nothing happens. See, palladium up here, nothing happens to the PFOA. But when you have hydrogen delivered and the palladium nanoparticles there. Then you get the loss of the PFOA, and you get the release of fluoride ion. Okay? So this happens all the time. It works with PFOA, PFOS. It works with the shorter chain analogs. It works with everything we've ever tried. Now, when you do this, what you get is a mixture of defluorinated products. And these are the spectra from mass spectrometry. But what's more interesting to just look at the graphs here, at the formulas. This is PFOA here on the left, and it gets reduced and reductively fluorinated to a mixture. In some cases, we remove just one F or two Fs, or some cases we removed all the Fs. So you get a mixture of defluorinated compounds, and they are then susceptible to oxidation. Now, that was a batch test. We also run this continuously. Here's a continuous one where we were feeding in about 0.4 parts per billion, and we were consistently getting out less than about 20, less than 20 micrograms per liter, or ppb on this. So this is, like you see, 70 days operation, and we've actually operated longer than this. So the process can run continuously for a long time. Now, once you have created these defluorinated products, then they are susceptible for oxidation, and we're going to use the membrane biofilm to get biologically catalyzed oxidation and more defluorination. So I'm just going to show you one result here of this. We've got many results, but I'm just going to show you one result here where we tried out the system. So what we did is we grew a biofilm. We grew a biofilm in our aerobic oxygen-based membrane biofilm reactor, and we fed it octanoic acid, the unfluorinated analog of PFOA. And over here, we ran it for like 140 days, and we had a nice biofilm. At that point, we added then 2 FOA. This is octanoic acid with just 1 fluorine. So that's really an easy one. And you can see here's the influent, here's the effluent, and you can see we got immediate removal. And the most important thing is these little brown diamonds, and this is the fluoride release. So we're getting oxidative defluorination and removal. We played around with the concentrations and loadings, and we always got 100% removal and 100% defluorination with this relatively easy compound. So armed with that success, we then said, well, let's make it more difficult for the microorganisms. So then we added 2-HPFOA. This is PFOA with 2 fluorines removed and 2 H's substituted in. So that's called 2H. And we added that in here at day 226. It's the same reactor. And you can see we got some immediate removal. That was just absorption. But then it took a little while, but then the biofilm started to adapt, and we started to see continuous removal and continuous defluorination. And as you can see, we played around with the loadings and did some different things, but eventually we got very consistent removal and very consistent defluorination here of this compound, which has only had 2 spots defluorinated. So this worked very, very well. So how does it work? Well, what these organisms are doing is they're defluorinating and doing that in concert with a very common microbiological reaction. It's called beta oxidation. It's one of the most common reactions in all of biology. It's simply where you oxidize a chain and you eventually cut off 2 carbons. That's an acetate. And so what you can see in this example here, this is the removal of our 2-HPFOA, and this is the production of C6. So go from C8 to C6 and removed 2 carbons. And we completely mineralized those 2 carbons on it. And you can see there's also fluoride release with it. So the microorganisms are oxidizing the carbon, and they're doing additional defluorination. And I'm not going to show you the result on this. I don't have time for it. But when we put the 2 together, we can get complete defluorination, and about half of the defluorination is in the initial palladium-based reductive defluorination, and the other half is in the aerobic biological defluorination stage. So it works really, really well. Okay, so I'm getting near the end, so I'm just going to give you my take-home lessons here on this. So first of all, we want to do reductive defluorination using palladium-based catalytic films in the hydrogen-based membrane catalyst film reactor. And as I showed you, it's very simple to produce these palladium-based catalytic films. It's an autocatalytic process. We can do it repeatedly. We have very robust films. It works great. We've documented that it will defluorinate PFOA. I showed you that. We've also done PFOS. We've done many, many other PFAS molecules. It works for everything. And once we get it defluorinated, then the oxygen-based membrane biofilm reactor continues the defluorination and oxidation, ultimately mineralizing and completely destroying the molecules. With that, I've come to the end. Thank you.
Thank you, Bruce. Appreciate it. We do have a couple questions for you.
Good.
First one is, given the potential financial investment for PFAS destruction, would you expect co-contaminant degradation of other micropollutants besides PFAS? If so, which ones?
Yeah, yeah. So well, first of all, the system that I showed you, the two-stage system, will handle oxidized contaminants, and common ones would be things like nitrate, or nitrite, or perchlorate. And then the aerobic one will handle all kinds of organics, any kind of organic you have in there that you'd like to biodegrade. Could be your natural organic material, or if you happen to have something like phenolics or something in the water, it would easily handle those.
Okay, next question has to do with the, like, where is this where is this technology most practical? The question is this better for something with higher PFAS concentrations like 10 ppb versus 10 ppt?
Yes, that's a great question. And it'll be technologically easier at higher concentrations. And so one of the focus areas we have right now is looking at reverse osmosis retentate. We think that's an extremely good candidate. And we're also looking at a number of industrial wastewaters, either from the manufacture of the PFAS molecules or for things like the semiconductor industry.
Okay, and the next question has to do with the byproducts that are being created from the process. Any thought about how to overcome those concerns? I assume they're
Yeah.
talking about the fluoride. I'm not
Yes.
sure.
Yeah. So fluoride is an issue if you're having higher concentrations. Now, if you're treating 100 parts per billion or 100 parts per trillion, then the amount of fluoride released is trivial, and you don't need to really worry about it either from the human point of view or from ecosystem point of view. However, if we're treating much higher concentrations in the parts per million level, then yes, then we would need to can be concerned about the fluoride, and there may need to be an auxiliary fluoride removal mechanism for those very high concentrations.
Okay, and then I don't know if any thought's been given to how this could be integrated into existing drinking water treatment plants, or if this more the application currently is more on higher different industries. Has there been any thought about how this could be integrated into a treatment facility?
Yeah. I mean, so I think that a lot of the answer to that question is depending on what you're trying to treat and to how low of a concentration. I mean, if we're trying to take PFOA down to 4 nanograms per liter and we're coming in at, parts per billion, it's going to be hard for any one process to get that 99.99% removal. So but this approach I think is really good for getting, say, 99% removal, in which case you might follow it with GAC, but then your GAC is going to last forever because you're putting on such a very, very low load to
Excellent.
GAC.
Yep, that makes sense. And then this kind of a flip to the question about the byproducts. Is there any thought to recycling or capturing any of the byproducts that are created with this process and then
Yeah.
reusing them?
Yeah, you really only create two products. One is inorganic carbon, and that's just going to stay in the water as bicarbonate. It wouldn't be worth capturing. If you really had a high concentration, you might actually remove the fluoride in some kind of recovery method, because fluoride, it's used and it's a valuable compound. So you'd have to look at the economics of that. I haven't looked at the economics of it, but you would have to have a pretty high concentration of fluoride to make it worthwhile.
Okay. And then one question I have is this Has this made it into any kind of commercialization? Is there any company that's looking
Yeah.
to, offer
Yes.
this?
Yeah, we have a spin-out company here associated with Arizona State University. It's called Metrics Water Catalyst, with their explicit goal of scale up and commercialization of this technology for PFAS.
Okay, fantastic. Bruce, thank you very much.
Very good.
This ends the first segment of our webinar today. I hope you enjoyed it. I certainly did. Looking forward to the second half of today. We're going to start at sharp 12:30 Eastern time. No, we've got folks from other time zones, but 12:30 p.m. Eastern time. We're going to have Megan Plumley join us for her talk on Perk Pond. So I'm going to stop the recording or pause it, kind of go off. We'll just yeah, pretty much stop the webinar for a bit, get some lunch, take a break, and we'll go from there. Bruce, thank you so much.
You're welcome. All right.
Appreciate
Bye-bye.
it. Take
Bye-bye.
care.
Groundwater system. Sorry, now I flipped away from potable reuse over to groundwater again. And then also looking at supercritical water oxidation, or SCWO, for destruction of spent ion exchange media used in those drinking water treatment facilities treating groundwater using ion exchange to remove PFAS. But again, back to in situ removal of PFAS during MAR. So as part of our groundwater management activities to do recharge, we have a lot of land area that we use for also have a lot of these man-made lakes or percolation ponds shown in the picture there on the right. This one's called Anaheim Lake near the city of Anaheim, where we divert the Santa Ana River water into facilities like this to allow it to percolate into the ground, which it does at a rate of about 3 feet per day, depending on the pond and how recently we last cleaned it by draining it and scraping the bottom and then putting water back in. Here's another view of the river with the off river, as we call it, section to the side there for percolation. And another view of the river in the background of this photo, and then some of the recharge facilities shown there in the foreground. So we know that water quality is improved during this recharge process through soil aquifer treatment. A lot of particles and bacteria and viruses removed, other dissolved constituents are reduced. But it's not a perfect filter, and it unfortunately doesn't remove the PFAS, which is probably no surprise to this group. And unfortunately, PFAS are present in low nanogram per liter quantities in our river water that we're recharging into the aquifer for ultimately drinking water purposes, down gradient where the wells pump the water out. So we are seeing impacts to a number of those drinking water production wells. So we've been in the process of building ion exchange treatment facilities on the ground at those different well sites for 100 different well sites across our region. So it's a huge impact, PFAS, to our region. We're building 68, I think, different PFAS treatment facilities. Since of those 100 drinking water supply wells that are impacted and need treatment, some of them are co-located close enough that it makes sense to combine them into one treatment facility, hence only 68 treatment plants being built, driven by regulation as far as MCLs. And before the MCL came out, we also had California response levels that was driving our journey through piloting and then treatment facility construction. But as an exploratory, essentially R&D question, we've been asking ourselves, could there be a way to remove the PFAS from our infiltrating surface water supply that's used for managed aquifer recharge at the surface by somehow engineering these recharge facilities like shown in the picture there? And how would that cost compare to what we are having to do meantime, which is construct these drinking water treatment plant wellhead facilities, which are essentially treating the PFAS after the fact, after it's made it into the ground through infiltration, and then as we pump it out to use it as drinking water supply, that's where we're doing treatment, conventionally with largely ion exchange and at fewer facilities, GAC. And I say it's a $1.8 billion question because that's how much we're spending to build these 68 PFAS treatment facilities at the various wells, or that's the cost number over, the capital plus the 30-year O&M life. So our partners on this project, we got a research grant from the U.S. Bureau of Reclamation, and then we are working with Colorado School of Mines as advisors on the project, PFAS expertise there, and also Jacobs. Scott Greco will be speaking later today, I think, and he's a partner on this project as well. So the basic concept we have envisioned, kind of a wild idea, is that, well, first, here's a picture, a simplified cross-section of what a surface water infiltrating pond would look like. So, of course, the water, it's just a terminal pond where the water goes down through the soil, and we know that PFAS is minimally removed. So the idea of this kind of crazy idea is, could we install a horizontal layer of PFAS? So I think of it as a permeable horizontal absorptive barrier. Could we install something like this a few feet down and have it be removing the PFAS so that the recharge water is PFAS free? And our back of the envelope calculations, with the idea of using Fluorosorb 200, the Setco product, as this, what's shown in gray here, layer. Our back of the envelope calculations suggest that given the low amount of PFAS in the water and the very low naturally gravity-driven hydraulic loading rate, the media could last many, many decades, potentially. So the concept here is no O&M, like you would have to do all the cost of installing the layer, but then once it's in place, you would just leave it alone and run your percolation pond as normal, and it would just last basically, essentially forever. You wouldn't be, excavating down, digging the Fluorosorb out and putting fresh media in over the life. Soil columns to simulate that upper layer of native soils. And then we've also built larger scale test cells, where we essentially built these concrete basins that we had existing concrete basins that we retrofitted for this project to simulate estimating of a full-scale concept, and then separately these demo scale test cells as more of a proof of concept kind of miniature version of a real basin. And now I have some fun pictures to build those demo scale concrete test cells, trenching to bring the water over to where those test cells were already located. And here they are, so you can see how large they are. It was 26 feet by 8 feet, the different cells. Filling them with the, I think not pictured here, the Setco material, and then this I think is the native soil going on top, and ultimately filling them with the water. And they've been running for several months, more than a year. Can't quite remember the number off the top of my head, but quite some time. So just jumping quickly to our results. Excuse me, something in my throat. So we simulated as a theoretical concept, imagining like a 5-acre sized recharge pond, so terminal pond, and envisioning if we installed 4 inches of bed height of the Fluorosorb media, that would be below a few feet in native soils. So in the table there, it shows you, how much media we're talking about, and our estimate of what that could potentially cost, depending on the price per pound of the media. Maybe we'd get roughly 10 million, and then I'll just quickly go through this, but go work on this out, take data.
So yeah, experienced a little technical difficulties here. Megan, I don't know if you can hear me. I don't know if you want to just maybe stop, maybe leave and come back in. I'm having
I'm
trouble
back.
here.
Can you hear me now?
Yeah, I can hear you. Yeah, I don't know what was
Okay,
going on.
yeah.
We lost you a couple times. We lost your screen share. Do you want to? I turned your video off. I don't know what else to try, but maybe
Darn
let's
it.
just see. Let's
Okay.
just see how we do. Maybe just start with just that last slide. We couldn't hear anything.
Are you seeing the screen or should I share it again?
Yeah, if you could share it again.
Okay. My mouse is also not working.
This is
So
always.
this is awesome.
I mean, here
Okay,
here's
let's
another
see.
option too. Is I have your presentation. I could pull
I
it up
think
and
I
share it.
almost have it. Yeah.
Okay, okay. We do have a backup. I could pull it up on my end.
You see
There we go.
the slide
Yeah,
yet?
yeah.
So you want me to start over with this slide or the one
Yeah, I think
before?
this one is where, yeah, we didn't get all of this. So if you want to just start over on this one,
Okay, sorry about that.
that's okay.
So just jumping quickly to the results. So if you look at the right-hand side table, so we imagined one of our 5-acre recharge ponds, and based on our results, how much media we would have to install, and what that would cost. So you can see it's about $10 million worth of Fluorosorb 200 media to put 4 inches buried about 3 feet down into one of our ponds for a 5-acre size. So, quite a large cost. And based on that amount of material, with the left-hand table there, which I'll walk through quickly, we can estimate how long this media might last to remove the PFOA as a target compound. And how we got to this number with Scott Grieco's help from Jacobs is really looking at our data from those pilot columns that I showed, where you had to wait quite a long time to get PFOA breakthrough curves for different EBCTs in our study, and he essentially used that to evaluate capacity of the material for PFAS and project that out to this imagined hypothetical full-scale installation, what the life might be. And without kind of going through too much detail in the table, it depends on what kind of hydraulic loading rate we assume, which is numbers representative of our percolation ponds, and what the water quality objective is. Are you trying to get non-detect PFOA or maybe the time point to 50% exhaustion? And okay, I'm clicking and it's not. Oh, there we go. So right now, based on the numbers we have, it's a little bit too wide of a range, too much uncertainty. We think media life could be anywhere from 17 years to that 100 plus years we were initially hoping for. So essentially what we're doing is collecting more data.
Yeah, we lost you again. Sorry about this, folks.
For as long as possible. I won't get into more cost details here, but when we compared these costs to the more conventional treatment facility construction at the production wells, overall, it suggested to us that PFAS removal and update our final analysis and then publish those findings. So stay tuned. Thanks.
Thanks a lot, Megan. Really appreciate the presentation and all the work you've been doing on PFAS. Anybody who's been following PFAS research in the U.S. knows that Megan and her team and the firms that she's been working with have been super helpful in identifying good solutions. So thank you for all your work. So why don't we jump into some questions and we'll see how we do with the audio. First question is, does Fluorosorb require an activation phase before actually removing PFAS? Are you concerned on biofilm form? So two parts. And then are you concerned with biofilm formation reducing PFAS capacity?
I don't believe the product requires any sort of I forgot what the word was, but pre-activation or to ready it for use. We just directly put it into use in the pilot testing. Um, and then as far as biofilm, I think there probably would be some, natural amount of biogrowth. Our prime directive is to recharge water. We want have a good high percolation rate. We wouldn't want this layer to impede percolation, so that is a key question. And so I think the biofilm question kind of fits into that. Based on the hydraulic conductivity of the material, it's even more conductive than our native soils. So despite it being technically a clay-based product, we're not really worried about impeding recharge. But part of the reason we wanted to build those concrete test cell systems on a larger scale was to essentially build a realistic system and then just run it for a really long time and see if we have clogging problems. And we don't see any clogging issues relative to what we would normally see when there's no layer of Fluorosorb installed.
Great, thanks. Yes. Next question is the report and are the report and the results available detailing the breakthrough and the calculations of media life? Is that in something that's been published or could be shared?
Yes. Yes, we delivered a final report to the funding agency, USBR, and I think they post the reports on their website, but I don't know that this one's up, and I'd have to confirm that. So we're happy to share it. We think the kind of quote unquote real results will be in our future scientific publication, because that's where we would have more of the updated numbers. But as far as the approach and calculations, that's certainly available now in the grant agency final report.
Great. Next question. What's the purpose of covering the Fluorosorb with native soils?
So, in our current percolation ponds that are, of course, native soils, we have to clean them every now and then to maintain percolation rate. So the ponds are drained and they go in with heavy equipment and scrape silts and fines off the top. And then it looks like beach sand again almost. And then they put the water back in and it perks great for several months. So the idea is you still want to be able to do that, right? So if we bury the Fluorosorb 3 feet down, then the guys could maintain these ponds normally and clean the silts off the top. Whereas if you had the Fluorosorb laying right on top, it would be getting clogged up with the silts, and every time you scraped it, you'd lose some of your expensive Fluorosorb.
Thanks for that question, Adam. And then the last question from the participants, are there any other materials similar to Fluorosorb? Is there a competing product that has, could be used for the same purpose? Is it Fluorosorb or nothing? Is there anything else out there?
So I definitely think one could consider other medias like GAC, or anything with, or even the potentially the ion exchange, as long as it had that hydraulic conductivity with the gravity fed system. So I'm less sure about that for ion exchange, whereas maybe something like GAC. The reason we zeroed in on Fluorosorb with initial back of the envelope calculations was in our pilot testing in a different application for our groundwater, for our surface water impacted groundwater, we were seeing that Fluorosorb had the longest or tied for the longest media life of any
Hmm.
product that we tested compared to ion exchange and GAC. So it just seemed like it had a really long life and high capacity for PFAS. And that's why our back of the envelope calculations suggested we could maybe even get 100 years of life in an application like this. But Setco does offer other types of Fluorosorb with variation in material size or blending. And so that's something we've thought about testing as well in case something else could be more suitable for some reason.
Fantastic. Yeah, thank you for excellent presentation. And like Bruce Rittman's presentation, this one was a little bit maybe off, not particularly focused on surface water, but I thought there is a possibility for surface water applications and just the novelty of the research. Just it's something that folks who maybe have both supplies could think about. So, Megan, thanks so much, and thanks for all your support of research on PFAS. You and your
Thank you.
team. Thank you very much. Okay, we're gonna move on to the next presentation, number 6. This is Chris Kern. Welcome and go right ahead.
Okay, AJ, can you see my screen?
I can.
Great. Thank you all. Happy to be here today to talk about some of the hidden plant impacts and operational considerations associated with surface water treatment for PFAS. So I'm going to talk really high level about surface supplies and how we go about treating PFAS, some of the topics you've heard earlier today, some operational considerations and drivers, and then conclude with a few case studies. Okay, so starting with, how we approach treatment in surface water supplies. There are a number of different parameters that really drive the difference than from treating like a groundwater source. One is the scale. Typically a lot of surface water plants much larger in scale, flow rate than what we find in groundwater. Driving force predominantly, as we've heard today, is gravity flow. So when we're integrating PFAS treatment into that treatment train, that's a big consideration. If you're trying to avoid pumping, but as mentioned earlier, a lot of times pumping is going to be a requirement. The contaminants, there's a lot of variability. Seasonal, rain-induced, in natural organic matter, turbidity, inorganics, the synthetic organics like PFAS. That we find the concentrations are much lower here than typically what we see in groundwater. So a lot of times just above the MCL level and large in scale, and we have to manage the PFAS still for compliance. And then treatment technologies, a lot of traditional conventional treatment, pre-treatment required for surface water supplies. We see membranes, which is different than more of the pressure vessel type approach, absorbers, air stripping that we see in groundwater. So when we look at some of the different treatment technologies available, we've talked about some of these PAC. We heard some examples. I know we're going to have some other discussions around that. Granular activated carbon, ion exchange, and then RO/NF. And in the surface water application, we see a little bit less of the RO just due to some of the points mentioned before about economics and fitting that in. Usually there's another water quality driver present. In terms of some of the innovative treatment approaches, we are seeing, an opportunity for novel adsorbents. Megan was just talking about one. I'll touch upon that in applications in certain sources where there is competing organics due to their ability to be selective for PFAS adsorption when other background organics are present. And there's a number that are commercially available and a lot in development right now. There's some hybrid approaches where we combine GAC and ion exchange is part of a treatment train, depending on objectives, water quality. And then touched upon earlier, we're seeing some traction with separation destruction integrating into the water treatment space. It's typically been reserved on smaller flows, but there are opportunities. Foam fractionation was mentioned where the technology is beginning to scale up and opportunities which could potentially lend itself to some surface water applications. Fundamentally, for all these, though, with surface water, we really recommend piloting just to see that seasonal variation and variability and its impact on an approach. And we've learned a lot through our piloting at surface water facilities. I'll talk about one example here, some piloting observations where we're deploying an ion exchange, a couple ion exchanges in column testing for a surface water supply. In this instance of 40 MGD, but we've seen similar results at other locations as well. Typically the resin manufacturers recommend, will discourage backwashing of the resin just due to the preserving that mass transfer zone through the column and due to the similarity in size of the resin beads that can get all mixed up following a backwash. But what we were finding in our piloting was an accumulation of head loss going through the resin. So we, took use of the pilot to see, okay, what can we do to restore this hydraulic capacity? Because we really want to get to that PFAS removal capacity that we really see demonstrated in other testing on groundwaters, things like that. And so we, at first approach, we conducted some field activities. We scraped off the top 3 inches. We cleaned that media, put it back in to the top to see if we could, restore hydraulic capacity. We even installed cartridge filters. Initially we were trying to test this in a mode to be a tertiary process following media filtration, because we didn't want to have a large number of pressure filters preceding the ion exchange, just the practicality of that at scale. So we wanted to test that, but when we found that we were getting a lot of head loss accumulation, we did install cartridge filter ahead of the resin columns. We did continue to then notice biofilm development within the media, within the tubing, that was creating problems for the resin and achieving very high terminal head loss that wasn't able to be restored. We even used chlorine and did backwashing, and still we're at terminal head loss, so I had to discontinue the piloting. So just an observation in these surface water applications, it's definitely worth piloting to see if it's practical for your water supply, just to make sure you can get those long-term media life that is what's preferred with resins. We also looked at novel adsorbent. We've looked at a number of them, but in this example, this is the Setgo. It's their FS200 product as well. What we did observe in this, we got a little bit more life than the resins, but we did start to identify some head loss development in the media. We were able to backwash this media, and we had done that on a typical 1 to 2 week type um, frequency, but we did start to see some accumulation of head loss. We observed pucking, media cohesion of the FS200 in the column. So we started introducing air scour, and that was able to restore our hydraulics and continue with the pilot there. In other applications, that air scour really wasn't able to free up the cohesion that was observed. So we actually terminated that column, and we switched to an FS400 product, which is a larger grain material. You sacrifice a little bit of the PFAS capacity, but improvements with the hydraulics were very significant, and we've been running the column pilot since, which is routine backwashes, and it's performing very similarly to GAC. So that was an approach that we could do to make that a viable option in surface water. So I'm going to talk a little bit about operational considerations, drivers. So when we're looking at large surface water facilities, there are a number of different things that really drive, what's the best solution. Is it a lead only? Traditionally, PFAS treatment is always lead lag. So you can optimize that media life within the lead vessel. When you're talking scale, oftentimes with so many parallel trains, and you heard it earlier today about staggered approaches, we're able to still, assure compliance downstream with just a lead arrangement only. And that really helps a lot just with the space required on the site as well as cost, if we're able to manage it in a lead arrangement only. Other considerations, gravity adsorbers versus pressure vessel, and each have some benefits from constructability that need to be considered, site availability, site constraints, how it fits into the hydraulic grade line. The flow basis, do we design it for the average daily flow, like more of a peak month, or the ultimate design capacity of the treatment facility? All these are critical questions. Is the regulatory body going to allow for some peak bypass, assuming your blended flow just for those short periods of higher flow, as long as you're still compliant at point of entry. So all these are factors that need to be considered. Also, the number you have spare. We heard about the length it takes for doing backwashing, for taking media out of service, for filter to waste scenarios. So having N plus, 2, 4, what is the utility comfortable with, to allow for that. And then, as been discussed earlier, there is a lot of benefit of staggering the media so that you don't have all of them exhausting at the same time. That would just be a significant operational burden to go and replace all that media at the same time. So those are some of the considerations. Also, PFAS is the first major treatment changing regulation that we've seen in a generation at water treatment plants. So a lot of our facilities, space is limited. So introducing this new PFAS treatment in a surface water can be very large in footprint. So, retrofitting of existing filter bays is an option to some utilities, especially if they have some excess capacity within their existing filter beds and adequate depth for installation of the GAC. But, with the modification of under drains, you can potentially provide sufficient empty bed contact time within existing beds to get not only the turbidity removal that's still required in this filter absorber arrangement, but also the PFAS removal. So this could be a potential opportunity at some utilities and be a big cost saver. The one thing just to be aware of, especially if going from a mixed filter bed to a carbon-based, is the filter runtime frequency is going to compress just with the smaller grain media. There's more head loss, as mentioned before, so you really have to do some gravity-based piloting to make sure that your hydraulic grade line can accommodate it, or implement some pumping. And the unit filter run volumes will reduce with the carbon-based approach, but things that may be palatable with a particular utility. Other site considerations is just location of the vessels. We had a site actually out in Orange County, California, and a complex residential area where it was preferred to keep the vessels out of the view shed of the surrounding community. So recessing of pressure vessels is something we've done at a number of facilities, whether it's a building height restriction in an ordinance, or looking to blend better into the community. So that's a site constraint, site consideration that has to be considered. I know we're going to talk later today or tomorrow about residual management, but just some findings we had. A large eastern U.S. water treatment plant had PFAS levels, in the 1 to 2 nanogram part per liter in the raw water. So it wasn't a compliance issue for this facility, but they had historic lagooning of solids at the facility where solids have been accumulating, 8 years or so. And when you look at the filtrate from that residual that's been stored for a number of years, we can see some elevated, it's not significant level of PFAS like biosolid level, anything to that degree, but you can see some of that PFAS collecting in those residuals. So just something to be aware of, depending on how regulations in the future track. Also with DAF residuals, we understand that PFAS removal is not significant or reliable in terms of compliance, but we have observed some concentration factor of PFAS just in a traditional DAF sedimentation process. So again, just something to be aware of. They're not at concentrations that are causing any issue, but because of that preference, as we see in foam fractionation for that air-water interface, you can get some of the long chain compounds to move out with the float from the DAFs. So I'm going to talk about a few case studies right now. One is a hybrid system approach where we had carbon and ion exchange in series for Madison, Wisconsin. The treatment objectives here were non-detect PFAS in the finished water. It was a plant retrofit, so space was very limited at this location. And one of the drivers was there were background organics present in the source water. So in this instance, because of the retrofit, because of the end criteria of trying to achieve non-detect, a carbon lead with a lag ion exchange resin vessel was implemented. It's been in service for about a year now, with the GAC media still removing the bulk of the PFAS. We're starting to see some of the short chains come through, but the resin's there to be the main removal for the PFAS present in the source water. The second case study I want to talk about is Tri-Town, Massachusetts regional water treatment facility. It's a reservoir supply, about 13 million gallons per day, with PFAS ranging in the 20 to 30 nanogram per liter range. It's going into startup and operation right now. In looking at this and how to integrate treatment for PFAS, we looked at a number of different scenarios, some of which was tertiary um, slipstream treatment, side stream treatment with carbon or resin. But we also looked at the filter absorber approach using carbon for both the turbidity removal and for the PFAS. And because of a number of drivers here, there was also a TOC removal objective as part of this project. And at the time, the regulatory body was not interested in side stream treatment. So the PFAS treatment would have to be applied to the entire train. So the costs of that post-tertiary treatment were quite significant relative to a filter absorber approach. So the client moved forward with implementing filter absorbers. You can see in the upper right there a picture of the filter absorber installed. It was about a 5 foot depth carbon. We had to increase the surface area of the filter to get the target empty bag contact time, and it's going into service right now at the facility. Some of the operational considerations just during startup is that backwash, that initial backwash to remove fines is quite significant. You can see the images in the central is a typical DAF float. On the right, you can see the recirculated water from the backwash tank following that initial backwash of a filter bay. So all those fines were recirculated through the DAF and removed in the DAF, but you can see the magnitude of fines that are present. Also mentioned earlier today is that filter to waste, having provisions for that to waste any additional fines that may be present or any periodic elevated pH or arsenic that's bleeding off the media. To have provisions built into the design to address that. And going forward, since these are filter absorbers, just routine backwashing is necessary. And I talked about the frequency of that may be reduced in a carbon-based versus a traditional multimedia filter. So in closing, in terms of lessons learned, integrating PFAS treatment, as we've heard from a lot of others today, is a lot more challenging in surface water application, relative to groundwater. That scale and variability really needs to be looked at, those seasonal water quality drivers. And pilot testing is very, very important and informative for basing design around. So very, very involved. New technology really needs to be evaluated before, applying it large scale like that. So, looking at these novel adsorbents, looking at, maybe a potential down the road of foam fractionation in a large water plant. That testing is very important. And then building in operational flexibility is very important for these systems as well. And with that, AJ, I can take some questions.
Yep. Thanks a lot, Chris. Yeah, we do have a
Yep.
number of questions.
Okay.
So we'll just dive in here. First question was, how does the grain size of the ion exchange resin compare to GAC, for example, F400? And is there large scale experience with cartridge filter applications?
We've done large scale, like 10 MGD, 15 MGD on groundwater supply with pre-filters. Part of that is for any sand that could be coming out of the well, but not in a surface water application that I've done to date in terms of pre-filters for the resin. And in terms of grain size, typically larger than what we're seeing in the carbon.
Okay, we're going to audible here. We're going to allow an overage of time to allow for some answering questions. I think it's more important to get these questions answered, and we'll be a little late on the back end. But can you describe the protocol for resin cleaning when you remove the top 3 inches?
Yeah, and in the column, what we had looked at was we vacuumed off like the top 3 inches, to see if that's where the accumulation of the solids was happening. And we went through just a cleaning process and then put them back in at the top. We didn't, at that point, did not want to disrupt the entire bed and mass transfer zone. So we figure if we limit it to the top 3 inches, we could see if we were able to restore that hydraulic capacity. But unfortunately, it was not successful.
Okay, next question. Were the recessed vessels beneficial for hydraulics in that location, or did it end up needing to add new pumping or?
In that location, it really there was pumping already.
Okay.
But that could be a consideration, in other facilities, certainly.
Next question. In a lead-only scenario, are you allowing breakthrough and depending on dilution from other vessels to manage it, or assuming it will be recognized before it exceeds a limit?
It kind of depends. In working with some utilities, they'll set a point. If it's 3.5, and we've modeled different scenarios to see what that lends itself. But ultimately, if being held to the point of entry, there could be a little bit more flexibility there. But in the one instance, we were looking at maybe setting a change out around 3.5, because you would still have other beds that were essentially virgin carbon still, or replaced relatively recently, so that together you would still have assurance that you'd be meeting the MCL.
Next question. Have you considered or piloted Fluorosorb, the FS 400 or 600 for retrofits of existing filters?
Yes, we've looked at FS 400 in that scenario where I'd mentioned after the FS 200 was having the binding issue, we looked at FS 400. That was going to be still in a pressure vessel arrangement, but we have piloted gravity application of the FS 600 as well.
And stay tuned for a presentation tomorrow if you can make it, Tyler. There'll be a presentation on some work the commission did on that very thing. Next question. You mentioned that backwash can disturb the mass transfer zone. Did you observe early PFAS breakthrough after you attempted backwash?
At that point, we, when it was a fail due to just hydraulic reasons, we stopped sampling for PFAS at that point. It was pretty early on, so we had not observed breakthrough yet from the resin in the early samples, but it failed pretty quickly. So.
And next question, same asker. For FS 400, how much PFAS performance do you lose as compared to FS 200? I assume they're talking about bed volumes.
Yeah, there's a loss in PFAS retention. It's hard to just say, what that is across the board because it's going to be influenced by different things. But that's where, the piloting comes in handy just to see, what that looks like on the actual water quality. So it's hard to predict, but it is definitely a reduced PFAS retention, going with the larger grain.
And last question, for treatment plants looking to blend treated water with untreated water during peak flows, how are they determining what those flow limits will be? Are they looking at a percent of hourly flow rates above their max demand, for example?
Yeah, that's a good question. I mean, the EPA is based on a rolling annual average, as we're aware. But in cases of, these shorter term, we've developed some models before where you can just input those different variability in terms of what's your source water condition, how much are you treating, what's the removal, depending on your staggered where everything stands, and we can get to an idea of what that looks like. And in certain cases, some of the utilities we're working with have the ability to do sampling pretty quickly with their own lab and analytical tools. So we're able to get, a better understanding without having to wait, 2 weeks for results. So that definitely helps with that.
All right, Chris Curran, thank you very much. Really
Yep.
appreciate you presenting and all the work you guys have been doing. Thank you. We're going
Thanks,
to shift gears. There's been a lot of questions about residuals handling, and now we have a presentation on residuals handling of PFAS by Chad Corey of HDR. Welcome, Chad.
Hey, thanks, AJ. Thanks, Chris. That was a great presentation. I'm just kind of popping in here for this. This is a really great idea, AJ, to have this, state of affairs kind of internal conferences is fantastic. I'm really glad you could pull this together, and I'm glad to be a part of it. Just hopping in for my presentation, and then I'm going to jump back off. But other folks from HDR are on to kind of absorb it, take it all in. My sense looking at the agenda is there was a lot of focus on piloting and treatment. Definitely, we should be considering what's happening on the back end. Let's talk about PFAS residuals management. That's going to be an issue we'll all have to deal with. And to a smaller scale at some level, we're starting to deal with it now. Let's see here. Get the next slide. All right. Well, that's me next to a big truck. Little background, I've been treating PFAS since 2014. Previous life, I was a municipal engineer. I had the good fortune or bad fortune of having two clients adjacent to a military base and just swimming in AFFF. So I've been doing carbon and ion exchange since 2014, and it never stopped. So let's talk about residual. Let me see. Oh, you know what? You guys are probably seeing this. How do I get rid of this? Let me get that out of the way.
It all looks good.
Oh, you're all good? Okay. I couldn't tell if you were seeing my
Nope. Perfect.
okay, great. All right. So basically, how are we getting residuals? We've got PFAS being manufactured, it's being used, and then some form of pollution finds its way into the water supply, and we're going to deal with the aftermath of treating water and wastewater, and what the wastes are from the treatment system. So we've got multiple types of treatment: powder activated carbon, granular activated carbon, ion exchange type removal systems, and there's also membrane treatment systems as well. And basically, what this boils down to is you've got solid residuals to deal with, or liquid residuals to deal with. There are also gaseous residuals, and we'll touch briefly on that, but it's not really it's something that municipalities are going to have to deal with necessarily. All right, so excuse me, I thought I got rid of that. We're talking different removal processes. So if you see in the upper right, you got this big truck next to what we're all used to seeing are these pressure vessels. That's a 40,000-pound carbon truck. Half of that truck is now waste, right? Every time we rebed a filter like this, you've got 20,000 pounds in, 20,000 pounds out. What are you going to do with it? It's got a finite capacity, and basically, it's you've got two options. You can reactivate that carbon, or you can send it off to a landfill. And that's kind of a similar story for your novel sorbents and your ion exchange, especially if it's a single-use IX media. High pressure membranes, it's kind of a slightly different system where you've got a reject stream, which is highly concentrated brine, highly concentrated PFAS. You've got a couple options here. Preferred option here in the Northeast, because we aren't allowed to do injection wells, we're not close enough to an ocean to get a permitted discharge, would be treating that brine stream with carbon, and then you have a solids residuals to deal with. But there's a lot of it's pretty nasty stuff, when that comes out of these membranes. All right. So in the solid phase, we're talking landfills, or we're talking thermal treatment. Basically, finding yourself an incineration facility, and that could be through your environmental hauler. They'll basically have on contract their facility that they'll haul to based on your geography, and those facilities that can reach the appropriate temperatures to fully destroy PFAS are few and far between. So you could have, trucking is probably one of your largest portions of that expense, or a significant portion in terms of dollars per pound that you've got to dispose of. So we're looking at, you've got your spent media, that's most of your issue, and that could be the GAC, that could be your novel sorbents, that could be your ion exchange resins. You've also got biosolids and sewage sludge, which we don't talk about very much in this presentation, but it is something that on the wastewater side we will we'll have to address. But I think landfilling it right now is your best bet. For the liquid phase, we're talking about some underground injection or thermal treatments. And then the gas phase, you're looking at a scrubber or some sort of thermal destruction methodology. This is just kind of a highlight, of what I just said. Basically, these are your disposal options. You can reactivate, you can incinerate, or you can landfill, or you can do a combination thereof. GAC, you can get on contract with many carbon suppliers, including Calgon or Norit, and they will reactivate your carbon you lose about 10 to 15% through attrition. And they'll add some makeup media to your specific carbon before they return it back to your plant for reuse. That seems to be the preferred method for large scale GAC. Nice thing about it is it's a little bit more sustainable. You don't have to deal with the disposal costs, although the reactivation and handling costs are about the same. So, from a dollars per pound perspective, you're in a pretty similar scenario. You just don't assume the risk necessarily of that media ending up in a landfill that you're then tied to later as part of a Superfund cleanup type situation. Powder activated carbon, that's a little bit trickier because you've got a liquid that you've got to dewater. So if a lot of plants that they're using an interim treatment scheme where they're feeding large quantities of PAC at the head of the plant. You're really, every pound of solid that you're adding, you've got to deal with later. That's something you're going to have to handle. It'll have to be dewatered and either landfilled or dewatered and then incinerated. But it's, that I think of PAC as kind of a short-term solution for plants that are, maybe on the lower end of PFAS concentrations or even at or below that MCL. And this might be something like a stopgap measure to get you through a design phase of a more permanent solution. However, if you're consistently below the MCL, PAC might be just enough that you can add 100 pounds per million gallons or something for a temporary period of time to keep yourself just reliably and consistently below the MCL. And if you can manage that excess solids, then that's part of your prerogative. Ion exchange resins, most of these resins that we've been using have been single use, and your only option is landfill or incineration. I really do prefer incineration myself. I wouldn't want to assume risk of being tied to a landfill down the road. But there are regenerable brines that are coming onto the market, or regenerable ion exchange media that are coming onto the market, and that creates kind of like this, I don't know, more familiar ion exchange mechanism where, if you think of a nitrate treatment system or any other ion removal system, radiologicals or something, you're frequently regenerating that media. And then, that media has a much longer service life because this stuff's expensive. It's expensive to buy, it's expensive to transport, and it's expensive to get rid of. So if you can keep it and regenerate it, there's real savings to be had there. You just have to deal with that, with the regeneration brine solution. And basically it's either you hold on to it, dewater it, and dispose of those solids, or you can get permitted in certain states for deep injection well. All right. And then the same deal for the brine for the reverse osmosis and membrane filtration. So let's talk about some of the benefits and the challenges. We'll talk about solids, liquids, and gaseous wastes. So your solid wastes, landfill disposal. So that's probably the easiest thing we can do is take that spent media, put it in a truck, and find a landfill that will accept it. You've got a lot less. Well, the risk is reduced in that the PFAS is stuck to the media. You're not worrying about it leaching out on your property or on your facility. It's taken away entirely, and it's taken to a landfill. As long as that landfill has an adequate leachate treatment system, they're basically now they're on the hook to deal with any PFAS mobility after that. It's kind of an unknown, though. Right now that's acceptable, but regulations can evolve, and landfills may or may not be accepting PFAS-laden waste in the future. I think that's probably your biggest risk, and that points you toward the incineration avenue. And that's in a perfect world we would all incinerate, but you still. What are we doing? The fluorine's just going up into the atmosphere, right? And it's going to rain back down on us at 10 parts per trillion. So if we're comfortable with that, that's what we have to do. Solid waste, so disposal by incineration, you can incinerate almost anything. You can incinerate the GAC, you can incinerate the novel solvents, you can incinerate the ion exchange resin. Um, it's it's very expensive. I don't have dollars per pound in front of me. That seems to be a moving target, especially with transportation costs increasing. The fuel surcharge is probably one of the most volatile factors in that disposal cost right now. As you've seen in the last few months, the price of diesel has gone way up. It's starting to level off and come back down, but that's really impacting the price of handling these residuals. Um, and then you've got the question of, is it really destroyed? Do you have a reliable incinerator temperature that's consistent through that incinerator? You're not just at the point where they're measuring it, but through the entire volume of that incinerator that's reaching the 1300 C to break the carbon fluorine bond and destroy these PFAS compounds. And these are pretty resilient compounds. They were specifically designed to put out jet fuel fires that burn very hot. So they don't go without a fight. It's a difficult process to destroy them and get a complete burn. And then you've got the issue of what's the emission? What's the emission from these facilities going into the atmosphere? Some of those facilities may have a scrubbing system, but it's, really that the facility is dictated by the environmental disposal handler that you contract with. So they have their facilities that they like to go to, and they'll probably find one that's geographically closest to your treatment plant. Right. Reactivation. We kind of talked about this a little bit. GAC reactivation, if you're not familiar with if you're not familiar with the process, you're partially burning. I apologize. I keep getting the IM chats pop up. I hope you guys don't see those. You're partially burning that carbon to basically free up more pore space. It's probably been discussed ad nauseum at every conference we've attended in the last 2 or 3 years. But it really does reduce the volume of waste, especially when you get into the scale of some of these larger treatment plants. The 200 plus MGD plant that needs multiple millions of cubic feet of carbon that they're going to replace cyclically, throughout the year as they rebed their deep bed GAC contactors. That's a lot of volume of material to manage, and if you can reduce the amount that makes its way to a landfill ultimately, then I think that's a much more sustainable approach. It also reduces the demand for mining of the virgin GAC because your makeup is only that 10 to 15, maybe 20% that's lost through attrition. It could be lost through the incineration process. It could be lost in the shipping and handling. It can be lost in that, as that material is being transported down the road, you've got this truck, and visualize this, it's a truck bouncing along the highway, and carbon media is very delicate and very fragile. So it's basically being ground down from a smaller size. You start with a 12 by 40 mesh, and some of that carbon is actually being reduced to the point where it would fall through that sieve size. So after the regeneration process is complete, that carbon needs to be re-sieved. So you're only receiving the 12 by 40 or whatever your mesh size is back to your facility. So you're going to lose some just by the nature of the carbon being reduced in size through jostling and shipping and handling. Let's see here. IX regeneration. We talked about some of the benefits there and some of the risks in that you get to reuse your very expensive ion exchange resin media, but you've got to deal with the liquid waste on the back end.
Chad, we got about 5 minutes total, including Q&A. So
all right, I'm gonna rip. Thanks, AJ. Appreciate that. I'll rip through these really quick, and I'd love to take some questions. We talked about some of the liquid waste management. Here's a map up in the top right. The blue states are the states that it's permissible to get a class 1 injection well, like a deep well that you can return that liquid waste to the earth. I've got mixed feelings about this. I really don't like deep injection wells. I think you're basically short-circuiting a pollution back to the water table. We're not permitted to do that in Pennsylvania. That's where I'm located. And I think that's probably for good measure. I see mostly, Midwestern states, less populous states that, but in California, it's available too. But it looks like pretty much half the country, it's permissible or not permissible. And so in those blue states, you may be more inclined to look towards maybe a membrane treatment or ion exchange regeneration. All right, last slide. There are a lot of publicly available documents on best practices for residuals handling. Some of them are out by the EPA. There's a WRF 5285, which is something the HDR worked on, and I encourage you to take a look at those. There's a lot of great information there that I didn't really get a chance to go in the 15 minutes that we were discussing. So with that, I will open it up for questions.
Awesome.
Get the
Thanks,
screen.
Chad. Yeah, we
Yep.
got a few here. Feel free to add others in, folks on the call. So first one, are there regenerable brines for resins, methanol, ethanol, organic solvent, or are there any brines that don't contain any organic solvents?
Ooh, good question. I don't know the answer to that.
That's quite all right.
Yep.
Yeah,
Yeah,
that's
that's
a good,
a really
that's a
specific question.
that's a fair
But yeah,
answer.
yep.
Next question. Are you familiar with any regenerable IX products that do not require Class 1 Div 1 facilities for regenerate handling?
No, no, I'm not. I mean, unless you can, isolate that regeneration waste. Yeah, no, I'm not. Yeah, you're locked into it.
Yep. So it's limited by geography, it sounds like.
Mm-hmm. Mm-hmm.
So I had a question related to you mentioned landfills, but what about straight land application, dewatering, and then using it for um,
Yeah,
landscape
that's
materials or
sure.
some sort of
Yeah, or like
beneficial reuse?
beneficial reuse or Class A biosolids. I think that's a kind of a slippery slope. You think about what the criteria you need for Class A biosolids on the wastewater side. There's the wet testing. Um, I think that as those regulations evolve, and I kind of wish I had conferred with Stephanie Spalding, who's our biosolids expert. Um, that's going to be part of those criteria. I just don't see you making the meeting the criteria for land application of those solids. It could be permissible now, but it's something that I don't know if I'd want to take that risk of contaminating a farmland or even being, ethically speaking, I wouldn't want to eat the carrots that were grown in that field necessarily.
Yep, fair enough.
Yep.
Chad, thank you so much. Really appreciate it. Thanks for your flexibility.
Oh, absolutely. Absolutely.
And yeah, if Megan put an answer in on one of the questions, so please read
Perfect.
Megan's response. Thanks a lot, Chad.
Thank you.
So we're gonna go to our last speaker of today. Scott Grico is gonna take us to the end of the day here. So Scott, all yours.
All right. Thanks, AJ. You can see my screen okay?
Everything's good.
Perfect. Well, thanks. I think Corey had mentioned about a lot of piloting, and we're going to jump back into piloting. I wanted to cover piloting combined media in the same vessel, and we'll talk a little bit more about that in terms of PFAS treatment for surface water applications. So, good summary from what Chris had mentioned earlier. If you're listening to Chris's call, surface water treatment facilities are typically large volume gravity plants. So, between that and the background water quality can present unique challenges for PFAS treatment. That makes it a bit unique from groundwater. We often have to think about repumping through pressure vessels, but sometimes either because of scale or site constraints that may not be feasible. outside of the the negatives around the application, what you'd also see in a surface water plant is many systems do have existing filter media carbon filters for not only particulate removal but for taste and odor. When we're looking at carbon media deep vessels or basins for surface water plants, typically existing GAC can't meet that 20-minute empty bed contact time requirement for PFAS. So there are applications where we want to potentially maintain the GAC, but we also need to try to fit in shoehorn in the PFAS treatment. So one of the conceptual approaches that we've started to pilot is looking at applications where you may have existing filters. You could remove an appropriate amount of volume of the GAC and add to that a layer of a different material. In this case, we've been focused on Fluorosorb. Or if you're considering a new filter design and you still want to maintain the application of the benefits of GAC for taste and odor or disinfection byproduct removal, having a combined media filter could provide a design that's provides a shallower filter than what would be required if it was just GAC only. So that was kind of the basis of this piloting. As a few of the speakers have talked about, there is size differences between the Fluorosorb 200, 400, and 600. I will say that this was work that was done a couple years ago. So what we started with initially was the 200. We did realize that it is a smaller product. So what we did for this first pilot on the surface water in Colorado is we looked to potentially pick some arrangements and some carbons that would potentially fit well with combining it with Fluorosorb. So you can see the two different columns that we piloted. One had a layer of Fluorosorb on top with a denser carbon on the bottom, and one had a less dense carbon on the top with the Fluorosorb below that, supported on some sand media. And so we thought that would be a good idea to try to see, if we could keep the media segregated, in one direction or the other, depending on the placement of the Fluorosorb with respect to the carbon. So when we set up these pilots, step one was to add the GAC, either in column one or the sand and Fluorosorb in column two, backwash that media to remove fines, and then add the opposite layer on top, whether that be the Fluorosorb or the GAC on top, and then fluidize the complete column to not only re-stratify the layer below, but remove fines and stratify the upper bed and keep everything segregated. And what we found is everything mixed immediately after installation and backwashing. What I will say is because we had it this way, and there were, for this particular site, there weren't necessarily constraints to say this would be a bad idea. We actually ran this pilot initially, and I'll show you some data from that. So moving forward from there, you're moving on to 400 and 600. We stuck with the Norit GAC as a particular carbon, and you can see the effective size and the specific gravity of each of these media. So the carbon was a little bit bigger in size than the Fluorosorb 400, but less dense than the Fluorosorb 400. So bigger size, but less dense. Whereas the Fluorosorb 600 was a bigger size than the GAC, and it was also more dense. So on one hand you have the 400 that it's smaller, but but more dense. And on 600, it's bigger and more dense. And we wanted to see, which of these properties would really be the driver, assuming that the particle density would be the larger driver. So our goals for the second set of tests were necessary to look at PFAS results, but just to get the physical configuration that we wanted to achieve, which was eliminating that complete homogenization, maximize the separation between the layers, and be able to mimic full-scale operations. Achieve 20 to 30% fluidization of the combined bed. And so we took a look at those, but because the pilot columns are a little bit larger and a little bit more of a pain to remove the media if things combined, we went one other step backwards. And Setco that provides the FLUOROSORB material actually had 2.5-inch diameter columns available. So we had them layer a 50-50 blend of the GAC and the FLUOROSORB together, as you can see in those pictures. In backwash, each of them for 30 minutes, starting with a 6 gallon a minute per square foot backwash, and then ramping it up to 9 gallons a minute per square foot for another 30 minutes. Columns on the left, you can see are the starting points when they were loaded in. Columns on the right were after the backwashing. You can see on the left group there that the FS 400 with the GAC still mixed quite significantly, where the 600 stayed virtually separated and stratified from each other. So long and the short of it was that both the size and the density both do matter. So we figured that out and started to move forward with the larger scale testing. So this is actually redoing that same test in our pilot column out in the field. You can see after loading them and allowing each of them to be backwashed on top of each other, there is a little bit of a smear layer, if you will, between the two media, but in general, they stayed well segregated. We actually took each 1 foot lift and did an analysis on it to see how much of it was percent carbon versus percent FLUOROSORB. And once we got off the FLUOROSORB layer, none of the carbon actually moved into the FLUOROSORB, but there was a small amount of FLUOROSORB that went into that second foot layer, about 3%, and then above that smear zone, if you will, it was more than 99% carbon. So problem solved there. So that's pilot number 1. We did the same thing essentially at the same time at a different part of the country for a different surface water in Virginia. The selection of the FLUOROSORB at that time was the same, but interestingly enough, we selected a lower density carbon than what was used for pilot number 1 in Colorado. This carbon is an Evoqua or xylem carbon that's actually a subbituminous coal. It's a very, very low density coal. So difficult to tell from that picture. We didn't really get a good picture for the presentation, but it did have a smear layer, but it did maintain better separation with the subbituminous GAC. Long and the short of it is we'll talk about in the summary that the 400 and the 600 are definitely, especially 600 is definitely preferred for as we're moving forward with this type of application. But I do want to show you the performance of these columns, regardless of how well they were segregated or not segregated, because they we would expect that the performance to generally be the same. So from a PFAS removal standpoint, you can see here, this is the first pilot. This was the picture I showed you that was, essentially completely homogenized. That system was run comparing the GAC only in one column, FLUOROSORB 200 in the next column, which is in green versus that light blue. And then the two different mixtures of GAC, as I mentioned before, we started with the 400, the GAC 400 on the bottom, that got completely mixed. We started with the GAC 300 on the top, again, completely mixed. But you can see the performance there between the four columns. The combined column still performed much better than either of the medias alone. So we did see value in, in combining the Fluorosorb with the GAC. Interestingly enough, the GAC 300 looks to have performed, slightly better than the GAC 400. Not sure if there's a meaningful result there in terms of a bit of the later breakthrough, or if it was just an artifact of the pilot. But we do see benefit in that combined media. We took those data and we looked at what would be driving the change out for in the economics for a 7 MGD system. If you're looking at GAC, the GAC to meet the TOC target ran to about 40,000 bed volumes of the combined bed volume, but it broke through at about 19,000 bed volumes, based on the target PFAS PFOA at 3 nanograms per liter from that previous graph. When we looked at the Fluorosorb combined with the GAC, it increased the Fluorosorb breakthrough to be very equivalent to the TOC breakthrough. So it increased that total bed to be changed out about the same time as we would typically have to change it out for TOC. And so what that meant was that, the economics were, meaningful in terms of reduction in replacements, resulting in cost savings. Because the Fluorosorb does cost a bit more on a unit basis than the GAC, it's even though the bed volumes were essentially doubled, the cost savings wasn't quite in half, not only because of the relative cost of the media, but the differences in the volume of each of the media that's in the bed. So also wanted to provide similar results for pilot number 2. Again, this was a partially segregated media, so we wanted to take a look at a very similar system in terms of operation, but a little bit different. That there was a defined smear layer, if you will, but there was definitely evidence of plain GAC at the top, in plain Fluorosorb at the bottom. And for this particular plant, the PFOA was quite low, typically like 2.5 to 3 nanograms per liter. So we were focused on PFOS. You can see here that these are data that actually also include some ion exchange that we're not necessarily focused on per se in terms of this talk, but you can see comparative results. So, for the data on the PFOS, the carbons broke through quite prematurely compared to the other media, both ion exchange medias as well as the Fluorosorb and the combined. And the Fluorosorb started to break through, but we couldn't take it to its endpoint of meaningful results for the for the combined system. So what did help in that fact is we totaled up the measurable PFAS that were available. So this includes about 20 nanograms total of essentially shorter chain compounds on top of the PFOS, and you can see a defined pattern there where again the carbon Fluorosorb performance was actually quite good and lasted as well as the ion exchange media, if not even a little bit better, and certainly a lot better than either of the individual medias as well. So that's PFAS data. We were also very concerned, obviously, if we're going to be using this combined approach, there's got to be a driver for it. And, one of the drivers, as we talked about earlier, is TOC. this graph is reporting the running percent removal divided by the required removal. So a fraction of 1 is, the lowest target you want to be at. Anything below a value of 1, your required removal is greater, and your fraction is less less than 1. So you can see the line there where their finished water has an existing value. Just as a baseline, wanted to compare it to that, as well as how the different media performed. As you'd expect, the carbon medias, the GAC 400 and the Evoqua UC 1240LD, have very good TOC removal. But right behind that, obviously, because it's combined with the Fluorosorb, the UC 1240LD and the Fluorosorb are performing real well. Whereas the Fluorosorb in and of itself was similar to their current removal, essentially, very little additional removal of TOC and additional removal of potential disinfection byproduct precursors, which is what we would expect with the Fluorosorb. So, by and large, what these data show from this pilot is that we observed very good results from a TOC standpoint, as well as a very good result from a combined PFAS combination standpoint. So what we learned, the degree of mixing is definitely significant with the 200. It can be reduced or eliminated with different media and careful operation, meaning that the FS 600 is certainly a preferred product for less mixing. Combining that with lower density carbon will also be valuable. The mixing didn't necessarily compromise treatment, but it certainly could complicate issues if you're trying to regenerate your GAC. So keeping them segregated would be key for that point. And since we've developed these data that I've presented, we're currently piloting systems with functionally segregated media, if you will, and we'll be able to share those when we get results in the future. So with that, just want to acknowledge my colleagues that provided a lot of the real work for this testing, some of the testing done by Setco and providing the pilots through Intuitech, and of course the media suppliers. With that, I can take some questions.
Yeah, great. Thanks a lot, Scott. We do have some questions, so we'll go right into it. Question number 1, in pilot 2, was the total PFAS, PFOA plus PFOS, or was it other PFAS compounds?
It included a few other shorter chain compounds, and I'd have to go back and take a look at the data to take a look. I believe it was primarily, well, put it this way, from a math standpoint, the PFOA was around 3 and the PFOS was around 6, so that's 9. We had about 20 coming in, so there was definitely a smattering of PFBS, I think some PFHXA, and definitely some PFHXS.
Okay, next question. Have you had a chance to look at the permitting side of mixed beds with regulators for PFAS removal?
We have not explored that to any great degree from a practical implementation standpoint because we haven't gotten that far ahead. We've had some preliminary discussions especially with the regulators for the Colorado project, and that it certainly didn't. There weren't any immediate roadblocks in terms of any concerns, but certainly haven't driven it far down the permitting process, being that it's only being piloted right now.
Okay, next one. Are GAC media vendors receptive to reactivation when used in a mixed bed scenario, even with good stratification?
Depends on the media vendor that we end up talking to. The results are mixed depending on the vendor. I guess I'll just leave it at that.
Okay. Next, combining GAC and Fluorosorb via mixing or segregation led to longer media life than medias alone. Why is the sum of the parts more than the whole? Is it a bed volume plotting nuance?
No, it definitely isn't a bed volume plotting nuance. The primary reason is that although this is a suspected primary reason. Um, Fluorosorb is definitely more immune to TOC, but it's not completely immune to TOC. So having the carbon there to essentially protect the Fluorosorb from the TOC competition and uptake is one potential mechanism. The other potential mechanism is that, especially when you look at the example where we're looking at the totals, the Fluorosorb does tend to work better for short chains than carbon may. So carbon can take up the load of the longer chains and leave more room, if you will, on the surface. That's another potential mechanism of why the combination of the products are more than the sum of the individuals.
Next question. Are there any adaptations to be made to backwash systems to accommodate the GAC fluorosorb combination?
That's one of the things we're taking a closer look at. We haven't moved this into a larger scale pilot, and AJ will obviously be talking about this tomorrow. With just the Fluorosorb, but different configurations. I think it was Corey that had mentioned about potential air scour. Things like that can definitely help. Things that we're really not set up to evaluate in a 6-inch pilot, but certainly could evaluate in a larger demonstration in one cell for a large scale demonstration.
All right, part two. Are you thinking about aiming at a hybrid system, or would you prefer a lead lag GAC fluorosorb? Hybrid, I guess, being like all in the same filter, and then lead lag being two separate
Yeah, I mean, there's
units.
always applications for lead lag, and in that would typically necessitate repumping. We were trying to look for a creative solution for existing filter beds in the one particular situation, especially in the Colorado situation. We were really trying to solve a problem which isn't necessarily a unique problem, where they already have a GAC bed and they want to obtain the removal requirements for PFAS, but not have to extend the depth of that bed or change the operation, and maintain both the GAC configuration in that filter, as well as upgrade it for PFAS. So it was an approach to solve that particular issue, where you want to keep GAC in with Fluorosorb, and you really don't want to have to go to a lead lag situation.
Okay, next question. With the relatively low bar of TOC removal required, did you consider parallel treatment with some trains using GAC and some trains using fluorosorb media to achieve target goals? I guess that's similar to.
Yeah, I mean you could definitely play around with staggered operation and reblending, and that's certainly something that I think would definitely be on a potential alternatives evaluation to consider. It's something that we obviously didn't pilot, but it's certainly something worth considering.
And yeah, just a comment that the Fluorosorb product is NSF certified, so that's confirmed, right, Scott? That's an
Right.
NSF.
Yes,
Yeah.
that is that. Yeah, all three of those sizes are NSF certified.
And your last question, were there more pressure drop issues in mixed bed versus single bed?
We saw a little bit of additional pressure drop buildup in the mixed bed. That definitely was observed, and I think that's fairly common to see that with the Fluorosorb. But again, it wasn't anything that precluded operation of the pilot, or stop the pilot early. But we did end up having to manage that through backwashing.
Okay, great. Yeah, so thank you, Scott, for your presentation. Super interesting. Was really curious about what was going on in Colorado. We heard bits and pieces, but great to see the actual work. So thanks a lot for sharing that. Uh, And so, yeah, we're going to go right into the recap discussion. It's basically Adam, Scott, and Eric volunteered to be part of this sort of recap. I'm going to try to moderate as best I can and get feedback from you guys on different questions. And please put anything in the chat if you have some things that you'd like this group to talk about or things that you observed. We've got about 30 minutes, so we're gonna walk through a few things. So one of the things that I'd welcome your feedback on or your thoughts is I was surprised um, when I saw David Cornwell's presentation on the ion exchange bed volumes with the gravity application, no chlorine. We had been hearing about fouling, and Chris Curran brought that up in his presentation. Um, Curious, like the panel, you guys, any thoughts on why, you know, one why one place would be amazing and another place would be, horrible with more or less seemingly similar water qualities.
Well, I can speculate just a little bit. I mean, it the main culprit is typically blamed as TOC, which I think it was a fairly low TOC water. But beyond that, it was a pretty low loading rate. And if you look at the head loss graphs for ion exchange, they're proportional to the flow rate. So you have increasingly greater head loss at higher flow rates. And because he was simulating gravity application, the flow rate was only, if I remember correctly, was 6 GPM per square foot, which is right on the threshold where the ion exchange vendors recommend. It's the low end of the recommended threshold for ion exchange due to channeling concerns. And so that kind of allows the greatest opportunity for minimizing head loss with the lowest flow. And then if you looked at the total number of bed volumes, and again, I'm going from memory, I think it was up into like the low hundreds of thousands, like 130 to 60,000, if I remember correctly. And for ion exchange versus GAC direct comparisons, that's not necessarily far enough along that you'd have a cost advantage from GAC. I think that you typically start to see ROI advantages once you get up over 6 to 8 times the life of the GAC. So if your GAC was operating at 30 to 40K, then that's not going to be necessarily advantageous from a cost benefit perspective. So I think that I was surprised as well that he hadn't seen the head loss that he did, but those are some of the mitigating concerns I can think of.
Okay, yeah, Scott or Eric, any other thoughts on this topic?
Yeah, I guess the only thing I can say is anecdotally we've run parallel pilots with GAC and ion exchange right next to each other on 3 different water qualities and 3 different plants in the same region at the same time that have been pretty similar and seen drastically different results on the ion exchange between plants. I think that things that we don't typically measure potentially from a nuance standpoint, microcolloids and potentially even polymer carryover. I think those tend to have a bit a build up over time and potentially more influential build up on on the ion exchange resins than for surface water applications than I think we admittedly thought they might.
Okay, thanks for that. Eric, anything from you on this?
I'm just going to add the qualifier that I got back on late, even later than the question was originally asked. So I will step in, but I wanted to just add, because I think it builds on Adam's point about the break even on the costs, right? So when you have ion exchange that has to work so much better to break even on the cost, there's just more opportunity for risks of fouling and premature breakthrough or premature something to stop the ion exchange from working in the way that you want it to. And so that's the risk of, I mean, I'm assuming the question was around perhaps why ion exchange isn't used quite as often in surface water, but to me is one of the huge risks associated with implementing that technology in a surface water application.
Yeah, the basic question was we saw amazing results from David Cornwell at Passaic Valley, and then Chris Kern showing abysmal results at another application, and why such disparity? What's going on?
I would say though, even the amazing results should be taken with a grain of salt. That's all, because there's just so much that can go wrong when you're thinking about. I mean, I've seen results where it claims to have 5 years of life, but I don't know that I would trust that. Something's
Yeah.
going to go wrong in those 5 years.
Okay. The other thing, and I'll certainly give you guys a chance to make your own observations, but the other thing that I was surprised by, and I don't know if this is common knowledge, but David's conclusion that a lower empty bed contact time actually gets better results because of the NOM fouling. Is that generally well understood now? Because I'm thinking about like the way regulations are set up, and we have regulations that say you must have 20 minutes empty bed contact time, but that may not be
Well, I would
the
like
best.
to flip it a little bit, which is I think a little bit what David said because I've seen it. It's not necessarily that a shorter empty bed contact time is going to work better. It's that a really long empty bed contact time opens yourself up for that preloading of TOC and therefore shortened breakthrough, right? So he specifically mentioned, which is something that I've seen firsthand, that if you have like a design flow of 20-minute empty bed contact time, but then you're only running it at half of that, then you're looking at a 40-minute empty bed contact time. And when you think about it, oh, David joined. But when you think about it, you have loaded up so much carbon on that during the short period of time. And we saw this at HRSD when they were doing some work they call it, they had like a load of carbon that they babied because they were trying to, see how it would work. And they put really low flow through, and they ended up with just a ton of organic carbon fouling. And then their PFAS, once they cranked it up to a normal empty bed contact time, just blew right through. It lasted very short. So I would say they had even gone more extreme, and we're talking about 60 to 70-minute empty bed contact times on that thing during their short ripening period or whatever, during the long ripening period. But
Yeah.
I do believe what he said about the long empty bed contact times can be really impactful when there's high levels of TOC around.
We'll let David jump in here. You can take yourself off mute, David, and chime in.
I heard my name, and so I figured I'd better join. But from what I heard of Eric, I think that's right on. I think it's the longer that you have the empty bed contact times, especially when you're at lower flows in design and things like that, you can really start seeing some carbon fouling when you have some NOM issues. So I think that's a good point. I do think it takes a little stretch, maybe to convince regulators, I guess it's fair to say that you might want to operate at the lower empty bed contact times to get more life out of it. But I think there's some pretty good merit to it there. And I have to say, when I showed this to our friend we all know, Dr. Snowick, I showed him the data and he said, well, you got terrible NOM fouling. I said, yeah, I think so. So anyway, I'll just quickly on the ion exchange. Yeah, I mean, I don't think this is super performance at 140,000 bed volumes yet either. It probably doesn't even surpass GAC. I don't know, maybe someone had said that also.
Yeah.
Yet. I'm not facing my mic. But I do think we're not seeing so much fouling because it's a very short empty bed contact time of 3 minutes. But that's not a lot of data points.
Okay. All right. Thanks. Yeah, we are getting some questions in. I promise I will get to those. Just wanted to hit a couple other topics before we get to those items.
AJ, can I add?
Absolutely. Yeah, please. Yeah.
Just as far as PVCT carbon usage, I wouldn't have voted against taking those results as universal because they run contrary to. They run directly to the results that we've seen now from South Florida as well as the Cape Fear that I presented on. We co-authored a paper about utilization rates with EPA-ORD based on pilot results showing much better carbon utilization time. So it's certainly, I mean, think it's interesting. And it's one more thing to look at in your piloting, but I wouldn't at all advise it to be taken as a universal lesson.
Okay, yeah, and just a quick logistics. Maybe we couldn't hear you as that well that time, Adam. I think we got the gist of it, but maybe I don't know. Maybe turn the camera off or something. We'll see if it's everybody or just you. I picked up a little bit of that on David as well. It was a little fuzzy, but yeah, please if you can't hear people, let us know. We'll try to fix it. I did want to shift gears and talk a little bit about the one water or the one not one water but the one PFAS and looking at looking at this holistically and looking at the contribution of wastewater treatment facilities and where's the best place to do treatment. Something that the commission's been thinking about, and we have some information to share tomorrow. It just strikes. I'm just curious. It it sounds reasonable, but we don't have a regulatory sort of world where you get credit for what the wastewater people do. You have to meet the regulations. So I'm just curious, like, is the goal to try to bring all those people together and try to look at, joint funding for projects when it makes more sense to do it at, say, maybe at the wastewater plant or some other location. I guess I'm directing that to Eric and curious what other people think.
Sure. So AJ, that I'll just give you we cheated a little bit. So we're using the Aquacon system as a model system, which doesn't have a direct regulatory perspective, but has a history of over 50 years of cooperation between all of the entities, including the county, stormwater commissions and the wastewater plant, which was designed to be part of this reuse application, and then of course the drinking water facility. So we have an infrastructure that's already there, but what we're trying to do is prove out that it can be an effective strategy, like you were talking about, AJ, if you can get the correct collaborative effort involved. So we haven't, the great thing about it being a research project is there's really no like consequences of the answers. So we're looking through and we're creating the playing field and we're evaluating the performance of these different options and on the potential impacts at the water plant. And the idea is just to shed the light out there to say, hey, it would cost this much at the drinking water plant. It'll cost this much at the wastewater plant. We have one significant industrial user that is putting in a bunch of PFOA, who is actually in the process of designing a PFAS mitigation system, which will significantly drop it. We actually took advantage of a semi-controlled experiment where we were able to divert flow from that SIU away from the wastewater plant for about a month and evaluate the downstream impacts of the mass balance. So we saw all sorts of interesting results in there.
Yeah.
But and to speak to your point, like we haven't gotten everybody, but we created through this process we had the project advisory committee, we had the stakeholders, and then we invited this group of basically we call them observing partners, and it's regulators and commissions and folks from around the country that are involved in these kind of well, actually around the world, because we have a couple of folks from UK and Canada that are involved as well, that are involved in these kind of tied together source water protection systems. And they don't get to say anything, but they get to observe what's going on and see whether they like the model or not. So the approach is we're hoping to develop sort of a framework around, what can be done if you do have a potentially collaborative, non-regulatory, non-binding approach at doing, taking a look at this more holistically. It's a cool project.
Good work. Yeah, good work. So I'm gonna shift to the questions. I want to make sure the participants get their questions answered, and then I'm gonna jump back to any other observation you guys had on the information that's been shared. Anything that you thought was noteworthy. So these questions are to Adam about Cape Fear. Do they look at turbidity post deep bed GAC? And what does that look like before and after head loss backwash?
They do have turbidimeters there. I know that the turbidity is low. I can't actually comment on how the turbidity might change with respect to the backwashes when it's in service.
Okay. Another related question with them was Amanda asked, I know that Cape Fear has mid-depth sample taps, and I was wondering if there was a difference before and after backwashing, or if the sample tap was useful for evaluating the movement of the MTZ.
Yeah, I mean, we talk about, I don't want to split hairs between MTZ and just breakthrough front. But I think it's more useful for monitoring the breakthrough front, as in, the kind of how much GAC is actually experienced PFAS target contaminant PFAS loading. I think that the main part was just to acclimate to full scale in terms of when you expect to do changeouts. And those partial sample ports were relied upon really heavily in initial operations so that we could track, how much time they had before we were going to need to start changing out carbon. And the more experience they got operationally tracking the breakthrough frontier and how it associates with the water quality that they're treating, the less reliant they were on those partial sample ports. So I don't want to say they're never used now, but they certainly are used a lot less when they were at startup, when they were trying to track very closely how much life do we expect to get out of these contactors.
Okay, and then this question, which is kind of going back to our early discussion about empty bed contact time. The question is, besides EBCT, is there a filtration velocity which is considered optimal? I assume we're talking about GAC, but I guess you could comment on ion exchange as well. Anybody?
I mean, there's a surface loading rate and an empty bed contact time. So, I mean, I guess you typically don't do it in terms of velocity, but surface loading rate is a velocity.
Right.
So,
What
yeah.
do you look like? What kind of surface loading rate are you? What is considered optimal? Any thoughts there?
So I think
Yeah,
I've
I mean,
shown the
what are you
feelings
guys running at for the gravities, Adam? What's Cape Fear running at?
So the thing is, right, you've got your design EBCT and your design hydraulic loading rate, and you can't independently control them, right? So if you change one, you get an impact to the other.
Sure.
And I think that at least my gut, and I think where the data shows, is that for GAC, the EBCT differences are more profound in terms of impacting optimal media life than the loading rate itself. And like I said, at least in our experience, higher EBCT most of the time translates to a more effective bed life. So did I say that right? Lower EBCT, better bed life. For ion exchange, I think there's a lot of data out there suggesting kind of the opposite. I know Dr. Nappy's group at NC State has published a lot about the efficiency of contaminant transfer from the solution to the sorbent being governed by the thin film on the excess of the media itself. And so at higher loading rates, that film from the hydraulics perspective gets compressed, and so you get a more effective mass transfer gradient, and so you're actually able to load the media more effective from a contaminant gradient perspective at higher loading rates. The trouble with that is that, as we've talked about, a lot of times the trigger for changeout of resins ends up being head loss and not breakthrough. So when you run at the higher loading rates, you can more quickly slam into those head loss issues. And so I think it's been difficult to kind of isolate what the best loading rate is, because if you're trying to balance the head loss versus breakthrough and they're pushing in opposite directions, it's very hard to generalize a best loading rate.
Just one quick clarification for Adam. So I thought you were saying that higher empty bed contact time leads to better PFAS removal performance.
For
Is that
GAC.
for GAC? That's what you're saying basically, right? Okay. Because
That's what I've seen mostly in my experience,
right.
which I again recognize is not the same as what Dr. Cornwall presented on this morning.
Yes, yeah. So that leads to questions and getting to the bottom of what's going on and site specific issues. But it's that's I think one takeaway for me is you can't there's lessons learned, but they're not always universal, can be universally applied. You have to really know what you're dealing with. And that came across in a few of the presentations. So we got through all the questions, and I just wanted to let you guys, Scott, Eric, Adam, any sort of reactions to what you heard today? Anything that you think is noteworthy or is worthy of, some discussion or anything like that? Maybe we'll just do one person at a time. We can start with Adam, and then we'll go to Scott, and then to Eric.
I was not aware of the OCWD efforts to kind of deal with percolation water and the kind of cost efficiency benefits of that. So that was something I learned that I thought was interesting to recognize that there were some practical applications potentially there. That was one of the main things I learned, I think.
Great. Scott, any thoughts, observations, things worth discussing?
Shoot, he took my comment away. I not to make a shameless plug because I was involved with it, but to Adam's point, even though that's really not directly surface water related, combining that concept with the discussion that was going on with Eric, in terms of where the best place is to treat it, I do think that that's a very interesting. Not everybody has aquifer recharge and managed aquifer recharge, but to the point that you can remove it at the quote unquote source, cost effectively. That's one good example of thinking out of the box there, because I don't think there's a lot of other good examples where wastewater treatment is going to be all that effective or cost effective, so it's one good example of getting it out of the environment before it hits the drinking water source.
I just one follow up, because I was marveling at the prediction of years of operation, and looking at some of the data that we have that shows that biofouling, and there are things that definitely hamper the performance. So I'm just curious, is it because the water quality is so good, and then with that sand layer above the fluorosorb, that you're just allowing the fluorosorb to just focus on PFAS, and there's nothing, getting back to the work you guys did with the groundwater, you got really good bed volumes.
Yeah.
Is it all kind of related?
Yeah, I mean, in theory, yes, it is all kind of related. That's two things. One is you're hitting on a good point that the projections were based off the data we had, which are based off of lab scale columns at this point. As Megan mentioned, there's a field column out there, but in the great Stephen Wright comedian, he used to talk about the map that he had that was 1 mile equals 1 mile, right? And obviously we're going to have to wait, decades if that field operation that's operating at field scale is going to perform like we expect to manage aquifer recharge. We could be waiting for data for a long time. That's one of the reasons that that Megan emphasized having that native soil layer above the fluorosorb, because they do they do go through on a regular basis. Even now without the fluorosorb layer there, they regularly remove buildup and sediment on that layer, and so there's a management of the ponds that they've learned how to protect the percolation going through. We're hoping that to your point, AJ, we're hoping that is enough protection for that Fluorzorb layer.
Great.
Can I also add that I think it's pretty different I mean, obviously it's different applications, right? But just to put it in perspective, if you have 4 inches of Fluorosorb in a column and you're operating at 3-minute EPCT, that's roughly 500 times the loading rate, or that's 500 times the rate that you're talking about for 4 inches when you're doing 3 feet per day. So it's like a fundamentally different type of application.
The loading rate.
It's not
That's a
like,
good point. Yeah.
Yeah, and that's one that I don't remember Megan really diving into the details on it, but essentially there's a big discrepancy between running an isotherm, which gives you, full capacity of the material, versus a column. And to Adam's point, the percolation rate is so slow through that 4 inches that you're almost in that equilibrium state. So that's what we were trying to, extrapolate with the economics is how close are we to the pilot column versus the pure exhaustion of the media.
Yeah. I don't know if Megan's still on, if you want to add anything to this, but you're
I'm
welcome.
here.
Yeah, if you're welcome to chime in on the discussion if you like.
Thanks. I don't have much to add. I'm glad Scott's able to respond on the calculation. There was a lot of nuance in trying to scale up those column data that I showed the photograph of to project the life. So yes, Scott is going to update that further with our latest breakthrough findings. We essentially had to use more like short chain compound breakthrough to predict PFOA, if I remember correctly. But now we have the actual PFOA breakthrough that had finally reached a certain point in our columns. And so it's going to be, I think, a meaningful update to his calculations and projections, but it is still a projection because the challenge of our project is the columns have to, have a reasonable breakthrough time so we don't have staff waiting 15 years or whatever. So but yes, I agree with Adam's point that what's unique about our project is when you're spreading water over acres of land and letting it naturally percolate, it means the hydraulic loading rate is really low. And so that's why the back of the envelope pencils out to decades of media life, and that's what we're trying to fine tune to make it go a step beyond a back of the envelope calculation with our column data and Scott's projections. So
great,
it is pretty unique, but exciting.
Great. So Eric, any observations, anything you want to share on any of today's presentations? Anything else that you think's noteworthy?
You were going to let me off the hook with that conversation. I just wanted to put a little bit of context around a lot of this. I know for most of the surface water PFAS challenges that we've been involved in, it really is looking at removing 2 to 4 nanograms per liter of PFAS concentration at the expense of hundreds of millions of dollars in capital and then long range O&M. And so it speaks to kind of 2 things. And I think Dave mentioned this at the beginning, which was this idea that somebody may want to put in a quote temporary treatment system in the hopes that technology will evolve or something, or like we said, maybe there's more of a collaborative approach to management of PFAS in the watershed. And we're so close at some of these things that it feels like that really might be a way to responsibly proceed on this PFAS challenge. And I'm just throwing it out there because I think a lot of people talked about it, and there is a lot of, I don't know. I guess my main point on that is that, I want to go back to, I think I said this, and I think others did too, that surface water PFAS treatment is not the same thing as groundwater PFAS treatment. There's a lot more complications in it. And, just that's just a little bit of perspective, I think, at the end is what I wanted to provide.
Yeah, thank you. Yeah, you're absolutely right. There's a lot of lot of difference, and there's a lot more zeros on the end of the cost estimate. So
They're
it's a
bigger
big,
plants, right? It constrains us a little bit in our technologies, right? We've already talked a little bit about ion exchange and some of the challenges that it can run into. Um, it's not straightforward. There's operational issues. You think about putting out, tens to hundreds of pressure vessels, and that becomes really onerous really fast. Um, and then, so anyway, so it's just a thought, and I'm not in any way saying that we don't have to do this. We don't have to be able to meet those compliance deadlines. It's just that, um, there's multiple ways to think about it, and
yeah,
I I can't fault any utility for choosing any path that leads them to compliance, right?
yeah,
No
yep.
right answer. No
No,
wrong.
that's good. Yeah. So again, thanks everybody who presented today. Thank you for our panelists here this afternoon. Really enjoyed today. Hope it wasn't too much PFAS. Hope you got a little bit of a break in there. You can uh, reset your mind a little bit, but look forward to tomorrow. Same start time. Uh, and would like to get some feedback too on all of this. So feel free to email me or get in touch with me some other way. But thanks everybody for today, and looking forward to tomorrow. Have a great day.
Thank you.
Thanks Eric, Scott, Adam, Megan.
Thanks, AJ.
Chad's gone, but thanks everybody, and Chris too. Thank you very much.
Thanks, AJ.
We'll see you tomorrow, Sven.
See you.
Looking forward to it.